Hello everyone! Today's case is quite voluminous, so I suggest starting with the question: why should you familiarize yourself with today's case? Many of the listeners are already familiar with the terms cost engineering, value analysis, and reverse engineering, and for some, consideration of these concepts was even included in the educational program at the university. Therefore, these listeners will not see anything new today. But it's not that simple. To answer the initial question, it's necessary to answer a question of a different nature, namely, how does one cost engineer using such a tool as value analysis differ from another cost engineer of the same kind? The main difference between some cost engineers from others in this case is the classification of functions used in the analysis, which in turn there are quite a lot. I would even say that if desired, every cost engineer in the world can come up his own and thus form his own conditional analysis handwriting. The difference between the classification of functions proposed in our course from others, its orientation in terms of its content and formulation of functions to the formation of technical specification and design engineering support. In other words, our analytical handwriting is maximally focused on design engineering activities. The main differences between some cost engineers and others are: the first, the methods used to determine their significance and relevance, and the second, the methods used to determine both the degree of satisfaction and the quality of implementation. We have already discussed these concepts in the framework of the theoretical course and will return to them in future practical cases. Thus, returning to the original question, we can say that if you are interested in the issue of design documentation development within the framework of the design to cost concept, i.e. support for the development of technical assignment, 1D and 3D models by the cost engineering division, then today's case will definitely be of interest to you.
Practical case number 2 continues a series of issues devoted to demonstrating the possibilities of practical application of value analysis and value design engineering tools in various contexts, in particular in the context of reverse engineering and formation of product technical assignment or technical specification. The further presentation is carried out on the assumption that the students have familiarized themselves with the theoretical issues as well as practical case number 1, i.e. the issue of terminology of functional of value analysis and value design engineering will not be further accompanied by detailed explanation, as it was in the framework of theoretical issues. So, the general context of performing demonstration practical cases of development and reverse engineering using value analysis and value design engineering tools will be as follows. A certain developer company is opening a new line of activity, for example, the development of unmanned aircraft system. Accordingly, there is no groundwork in this area, i.e. firstly, there is no opportunity to spy somewhere other than in the publicly available information field, and secondly, the first approximation in development will obviously be the reverse engineering option. Next, we select a group of market analogs for which information about their theoretical characteristics is provided in open sources, for example, on the manufacturer's website, and their consumer functions are described in the terminology of value analysis and value design engineering, after which the technical requirements will be formed on their basis, as well as separate section of the technical assignment using the example of typical unmanned aircraft system for aerial photography and video shooting, which includes the unmanned aircraft vehicle, which with a takeoff weight of 250 grams. The final goal of the case is to demonstrate the effectiveness of the value analysis and value design engineering tools, not only in theory, as it was done within the framework of theoretical releases, but also in applied context using an example of existing market products. In this case, DJI unmanned aircraft system weighing 250 grams and their analogs. The audience that may be interested in the output analytical data of such an analysis includes the project manager and the chief designer. The methodology used in the case can be applied to the development of project documentation, pre-project, technical proposal, technical design, preliminary design, and etc., as well as partly at the stage of working design documentation in accordance with the GOST 2.103. The actual list of internal consumers of value analysis and value design engineering results is much broader and was reviewed by us in the framework of theoretical issue number 12. The external consumers of the results and the value analysis and value design engineering may include the investors if we are dealing with the venture project activities. In addition, the value analysis and value design engineering approaches demonstrated in the case can be used as part of the student learning process, for example, in the format of course or thesis, advanced training specialists from design departments, as well as cost engineering departments and similar headquarters units that accompany the development of new products in terms of providing information to the company management for making management decisions. Before diving directly into the description of the analysis process, let's consider the question of the terminology used. If we consider reverse engineering within the framework of classifications of type of functional analysis or value analysis announced in previous issues, where the value analysis is corrective actions against an existing product, and value design engineering is the development of a product with a certain degree of novelty, then we see that reverse engineering doesn't fully belong to any of these categories, since it includes themselves as elements of using data on existing product analogs, see the table of analogs discussed above, as well as the development of individual novelty elements, since the preparation of technical requirements or technical assignment as part of reverse engineering in most cases. One way or another we are faced with the need to make additional custom requests, basic and additional options, which we are not available for analog products. Since the format of the practical case avoids the conventions required for scientific publication, we can take some liberty and say, without burdening ourselves with a laborious justification, that another third type of functional analysis is added to the second classical types of value analysis voiced in the framework of short lecture courses, value reverse engineering. It's named value reverse engineering. Thus, as a result of this case, we will not receive a drawing of drawings with 3D models in USDD or in other standards, design engineering drawings, which I think was obvious, but we will receive a set of output data, analytical reports, and etc., which is formed in the real process of reverse engineering support from the value analysis and design department and value design engineering department. A list of the mentioned output data will be given in the column case description. Required services and output data in the standard form and table of general initial data, which will be discussed below. So, I would venture to be Captain Obvious and said that the modern unmanned aircraft system, hereinafter UAS, is a rather complex object of analysis, in particular in terms of required competencies in various fields of knowledge. Despite its modest size and relatively small volume of components, which can reach from several hundreds to several thousands, while, for example, such objects of analysis as a wide-body passenger aircraft, locomotive, or cruise ship can contain up to several million parts and assembly units. As in the previous issues, I will say a few words about the regulatory support for unmanned aircraft system reverse engineered process, which we will consider today. So, let's make a brief overview of the regulatory documents that will be used by us in formation of technical assignment. The first, the GOST 57258 unmanned aircraft systems, terms and definitions. This standard establishes the terms and definitions of basic concepts used in science, technology, and production in the field of unmanned civil aviation systems. The second, GOST 59517, unmanned aircraft systems, classifications, and categorizations. The description of this standard states that it establishes the classification and categories of unmanned aircraft systems to determine the requirements for flight safety, the required amount of work of certification of the developer or manufacturer of unmanned aircraft systems, as well as the rules for use of an airspace. The standard provides the following classification options. In section 5.1 of this standard, according to the maximum takeoff weight of aircraft as part of the unmanned aircraft system. The first category is from 0.25 kilograms to 30 kilograms inclusive. And the next category is from 30 kilograms. 5.2, section 5.2, according to the kinetic energy achieved by the unmanned aircraft vehicle in flight. First category is 100 joule or less, and second category is more than 100 joule. Section 5.3 for operational purposes. For types of operational purposes. First, for personal purposes, and second, performing aviation work. And the last, 5.4, according to the visibility conditions. 5.4.1, direct radio visibility, modes of full or multi-observer control and no visual control. And 5.4.2, absence of direct radio visibility. Further, the standard contains three categories of unmanned aircraft system, according to the description of which the objects of analysis belongs to open category A. It should be noted that in accordance with international official and unofficial standards, there are alternative classifications of unmanned aircraft vehicles and their unmanned aircraft systems by weight and other parameters, which the listener can be independently familiarize himself with open sources, in particular including first 6 classes, small, light, medium, heavy, combat and mixed. The next categories corresponding to classes, the next international analytical designations, the next name, for example, nano, micro, mini, and etc. The next range of action, the next is practical silent, and the last duration of the flight. For example, of the unmanned aircraft vehicle analyzed in our case with a takeoff of 0.25 kilograms belongs to the international classification of micro UAS, small class, first category, and the designation mu. The third, GOST standard is aerial transport, aircraft transport, unmanned aircraft systems, general requirements. The following standard applies to unmanned aircraft systems and contains the basic requirements for unmanned aircraft systems and their elements in the development, production, certification, and operation, and intended to harmonize and uniform approach to all procedures related to civilian unmanned aircraft systems. The next standard is GOST 59518, unmanned aircraft systems. Designing. Stages of designing. This standard was developed to establish the order and composition of work and the development of unmanned aircraft system for civil purposes. The standard is designed to improve the efficiency of the database development process. In essence, this standard belongs to a group of standards for various branches of mechanical engineering, which can be conditionally combined under the name development procedure, i.e. similar standards regulating the development procedure exist in the automotive industry, the railway industry, etc. The development concept generally corresponds to the concept of standard GOST 2.103, Unified System of Design Documentation, the development stage, which has been mentioned more than once in the framework of the theoretical course Cost Engineering. The next standard is GOST 59519, Unmanned Aircraft Systems, Components of Unmanned Aircraft Systems. This standard establishes the composition, specification of unmanned aircraft systems and general technical requirements for system components. In terms of general requirements, the standard refers to the standard GOST 5612 air transport, which we have already considered, unmanned aircraft system general requirements. Other information generally correspond to content of more voluminous documents, like GOST 59751, unmanned aircraft systems with unmanned aircraft vehicle of the airplane type, airworthiness requirements, adjusted for narrowed focus compared to all types of unmanned aircraft vehicles in general. From the point of view of applied design work, as well as the formation of structural and functional models, and then the corresponding technical assignment of obvious interests are. The section 4.2 contains information of the minimum composition of unmanned aircraft systems, namely the minimum set of components included in an unmanned aircraft system is as follows. First, unmanned aircraft vehicle, the second, the external pilot station, and the third, data transmission channel between the unmanned aircraft vehicle and the external pilot station. Depending on the task and operational category of the particular unmanned aircraft system, the composition of the components can be expanded. I suggest that we do not stop in other points related to the tests, the minimum list of maneuvers that the unmanned aircraft vehicle must perform. The last standard is the GOST 59520, unmanned aircraft system functional requirements of external pilot station. This standard establishes requirements for functional properties of external pilot station as part of a manned aircraft system, which I also suggest not to dwell on, since in any case attention will be paid to the functional properties of external pilot station in the technical assignment section, as well as a table of analysis that will be formed at the analysis stages discussed below. With this, I propose to complete the review of the regulatory documentation related to the chosen topic of analytical work and proceed directly to the analysis. Stage 1. So, the conditional first stage of analysis includes filling out by the analysis customer standard from called Table of Common Initial Data for analysis, which we consider in practical case number 1, 3D modeling and value design engineering, qualification, designation, initial data. Comment on the stage. As mentioned in practical case number 1, the standard form of common initial data can be filled in two versions, before NDA and after NDA, which differ from each other in that the other version, before NDA, firstly the name of analysis is not disclosed, secondly instead of numerical ones, the values in the columns in the form indicate the presence of absence data. In other words, if there is certain data, plus is put down, if there is no, minus is put down. The point of creating a variant from the form before NDA is that on its basis it's possible to pre-evaluate the availability of initial data for analysis of several product components and select the most promising ones from them. In terms of potential effect of the analysis, i.e. in fact the purposes of creating this variant in the form is to save resources for performing analysis. Accordingly, the graphs of the after NDA form variant certain the names of analysis in our case, basic products for reverse engineering, and also contain numerical data in the graphs that can be used in the analysis process. Otherwise, the options for filling in the common initial data table before and after the NDA are identical. It's necessary to pay attention to some differences between the form present on the screen, called Table of Common Initial Data, from the form that we considered in practical case number 1 of the course, Cost Engineering. In addition to minor adjustment in the wording of individual graphs and the general information block, the columns specifics of the analysis, the customer of the analysis, has been introduced. This innovation is aimed at immediately indicating the direction of the analysis, in other words, so that in the very beginning, even before the contractor makes a decision on the feasibility or unrealizability on the set analytical task, it's clear to whom the final report will be generated, the manager or the designer. The result of stage 1 is first, the formation of general or primarily impersonal initial data for analytical works in accordance with the standard form, and the second, the analysis of general or primarily depersonalized initial data and making a decision on the sufficiency and feasibility of analytical work on the part of the contractor and specialized internal division or external contractor. Stage 2. Second stage, which precedes the direct analysis, is the stage of forming a work assignment, planning a list and a budget of analytical work and task for preparing initial data in accordance with, firstly, with existing internal and external publicly available regulatory documentation, and secondly, taking into account the actual practice of performing the analysis. This case will be performed by analogy with the performance of one actor, i.e., the functionality of all specialists of value analysis and value design engineering division, see theoretical issue number 2 of the training course, will be demonstrated by me alone. However, in real life, most of the work, of course, is carried out in parallel by a group of analysts of the value analysis and value design engineering division. In connection with thus, we will consider an example of planning a list of the budget of analytical work for a full-fledged division. It's necessary to make a reservation about the references and regulatory framework used in the creation of standard form of planning, value analysis and value design engineering. Mentioned in this case of the course, Cost Engineering in general. In issue number 14, Value Design Engineering and Regulatory Support, Reverse Engineering, we mentioned the DIN 12973 standard with value analysis and value design engineering work plan, a set of forms, which provides a step-by-step plan for conducting the value analysis, the order and content of which differs significantly from the value analysis and value design methodology outlined in our training course. For the reasons stated in issue number 14. In general, this approach with strictly regulated standard forms is suitable for the case of automation of the value analysis and value design engineering process, i.e. the standard together with its forms, with the possible exception of the form of diagrams how, why, when, and several other forms, the applicability of which in practice, in my opinion, is extremely doubtful, can be transferred almost without preparation to a group of programmers for automation, as a result of which we will get a conditional software model, among other things, is positioned in DIN 12973. Okay, as a project management tool, which in my opinion is also very doubtful. As a result, I considered it appropriate to consider in today's case another forms from the DIN 12973 standard, but the forms given in domestic value analysis reference book, which firstly have shown their suitability in practice, and secondly, despite the vulnerable publication period, can be used with some modifications that take into account the changed level of development analytical application tools of functional analysts and design engineer and designers that differs from design engineer. F1 form is an initial document informing about the object, purpose basis, timing, list of participants, and cost associated with the analysis. Along with the definition of the goal, as a rule, there are restrictions under which the set goal should be achieved, comparative characteristics relative to analysis, limit values of the parameters of the analyzed objects, overall of installation dimensions, energy consumption, mass, and etc. Restrictions on the use of individual materials or technological processes, restriction on the creation of new types of production tooling, etc. In our example, the limitations is the degrees and the technical and economic characteristics of the functional and cost model developed by unmanned aircraft system by no more than 5% relative to the average value for analogies. This formulation of the limitation, about 5%, is based on statistics, according to which in reverse engineering a common phenomenon is a decrease in performance compared to analysis. The next form is F2 form, is one of the variant of a typical work schedule, which lists the stages of work, the content of the stages, and the responsible person and the deadlines. The next form is F3 form, is used to prepare a task for information support for analysts. In other words, it contains a list of initial data for analysis, technical and economic data of analysis, data on the characteristics of physical samples of analysis, information about the main consumers or target groups, and their degree of satisfaction with analysis, information on the quality of consumer functions for analysis. The responsible persons and deadlines for providing information are indicated. According to the results of the coordination of the list and budget of analytical works, see form from 1 to 3, formed on the basis of the table of common initial data before the NDA. The NDA and the contract for the performance of work are concluded. If the publication of an order on the performance of analytical work is included in the business processes of the analytical customer company, then in addition the above actions, the CEO, for example, signs an order to the creation of the working group. We will not single out in the separate stage of analysis, replacing the pluses in the form of table of common initial data before NDA with numerical data, since it's obvious that the order is just opposite, i.e. this form is filled with numerical values which are replaced the pros before being transferred to suppliers in the absence of the NDA, and the cons. Therefore, the complexity of replacing the pros and the cons with numerical data can be neglected. In order to diversify the process of presenting the case somewhat, let's digress from the technical side of our issue and consider the issue of consummate pricing. Judging by current market prices, the use of the concept of 1 kilogram of drone for the most popular consummate drones is quite acceptable in practice in the first approximation, since drones weighing 0.75 kilograms having a price about 190,000 rubles. The next drones weighing with 0.5 kilograms have a price about 150,000 rubles. Drones weighing 0.25 kilograms about 75,000 rubles. However, for cheaper models with a lower takeoff weight, this dependence ceases to be even conditionally linear, because firstly we are faced with a specific class of aircraft with a takeoff weight of less than 0.25 kilograms, which are characterized by such features as becoming gone with wind, the absence of a payload other than a camera, a reduction in the least function sensors, and etc. This metamorphosis on the basis of which they can be distinguished in a special category. Generally speaking, in scientific articles by foreign authors, this feature is carried out even earlier, namely at the level of unmanned aircraft vehicles weighing up to 2 kilograms. It is believed that unmanned aircraft vehicles weighing more than 2 kilograms have features similar to those of classic aircraft, such as the cost of development, operations, etc. With regard to unmanned aircraft vehicles weighing less than 2 kg, several other criteria are already being applied. For example, the loss of such unmanned aircraft vehicle is not considered critical due to its low costs as throwaway after use. Concept approach is applied of such unmanned aircraft, etc. An example of such an approach is the aimed forces of some countries is the registration of individual unmanned aircraft vehicles models not as aircraft but as ammunition. Looking ahead, I will say that today's case is subject of our consideration will be just conditional boundary of unmanned aircraft system with unmanned aircraft vehicle weighing 0.25 kilograms. And the range of analyzed models includes both conditional standards, DJI unmanned aircraft systems, and the unmanned aircraft systems, which can actually be attributed to children's toys, both in price and available functionality. Thus, the purpose of analyzing a similar, at first glance, absurd selection of analogs with identical takeoff weight is, firstly, the formation of universal structural and functional models which can be used for models of various price categories. Secondly, demonstration of the capabilities of the value analysis and value design engineering in the framework of the formulation of technical requirements or technical assignment. Assessment of the degree of satisfaction and quality of implementation of identical consumer functions implemented by different manufacturers of unmanned aircraft systems in different price segments. And thirdly, the preparation of analytical data based on information from open sources, i.e., in fact, an assessment of the complexity and possibilities of theoretical and practical approaches outlined as the lecture material of the course Cost Engineering. In the table of analogs used in the formation of structural and functional model, in addition to unmanned aircraft vehicles with a weight of 0.25 kilograms, DJI unmanned aircraft vehicles model range is presented a conditional standards in terms of satisfaction and quality of performance of function or quality of implementation in our previous terminology, including models Mavic 2, Mavic 3, Mavic Pro, Air 2S, Mavic Air. The list of analogs with a takeoff weight of 0.25 kilograms includes models Mini SE, Mini 2, Mavic Mini, and unmanned aircraft vehicles like Potensic Atom, Seafly, SGRC, Faith Mini 2, Xiaomi, FunSnap Diva 2 SE, and MGX Box 7. There is the most closest analog. The presented format, as I have already mentioned, allows you to generate technical assignment, then structural functional model, and other analytics in accordance with value analysis and value design engineering methodology. All the data presented in the table are taken from open sources, developer site, dealer sites, forums, and etc. Nevertheless, as we can see, even on the top basis of such measure, at the first glance, sources, technical assignment can be formed to the first approximation. In part, this is due to the fact that it formed from technical requirements or technical assignment, depending on what the developer was given access to data was taken to form a commercial description of the product. So in the case, we solve the opposite problem, i.e., combine disparate data from technical assignment first into a table and then into one document having a logical structure. We end up with the same technical assignment, of course, a stripped down form with partly distorted information, sufficient, however, in the framework of analysis or reverse engineering. In addition, some of the data from the original technical assignment can be restored by forming a weight sheet, which will be discussed below as part of one of the analysis stages. The results of the The results of the completing stage 2 is formation of the task of the execution of works, planning the list and coordination of the budget of analytical work, and the second, the signing of a work order of an internal analytical department, value analysis and value design engineering department means, or a contract for execution in case of analytical work performed by an external contractor. Stage 3. The first stage of analytical work is a collection of unstructured data on an Alex in accordance with the list given in the F3 form already discussed above. The collection is carried out by the analysts of value analysis and engineering department using all available sources of information, business trips, the use of software for technical benchmarking through the purchase and disassembly of an Alex, and etc. The results of stage 3 is formation of complete initial data for analytical work, a set of unstructured data on an Alex in accordance with the list given in the F3 form. Stage 4. The fourth stage of analytical work on functional and cost reverse engineering is to fill the table of an Alex presented on the screen based on information collected at the third stage. The information from this table will be used as subsequent stages of the analysis, in particular when filling out the weight summary, when forming the structural model, as well as when filling out the technical assignment. Thus, the importance of the table of analysis can hardly be overestimated. The experience of performing the analysis shown that it takes at least 30% or 5-6 working days to complete the table of the amount of time resources allocated in accordance with the schedule presented in Form F2, and the implementation of stages from 4 to 11. In turn, we will consider the features of the fourth stage of the analysis, which consists of informing a table of analysis based on data from the open sources. As I mentioned in previous issues, the data for the formation of advertising materials on the manufacturer's website, i.e. technical characteristics of the specification, if you follow international terminology, are not taken from nowhere, as you understand. I will give an example of where the pictures from the operational documentation for the product come from. As a design engineer, like all my colleagues, I was reluctant to spend part of my working time, which of course no one was going to pay for, interacting with specialists from the maintenance department. In other words, with specialists who form the contents of the maintenance and operation manual for the product being developed. In the labor market, these specialists are usually called technical writers. Obviously, due to the lack of necessary qualification or organizational problems, such as a lack of assets, etc., the specialist came and asked to make him several projections or 3D models so that he couldn't put down position on it with the names of part or components or individual units or systems. I have given this lyrical story for two purposes. The first is to make it clear to the listener exactly how conditional excerpts from the design documentation and design engineering documentation are formed, which include and above mentioned technical characteristics or specification listed on the manufacturer's website, and on the basis of which the buyer decides, or client decides to purchase of the product. The second one is to identify the second possible source of information for filling out the table of analysis, namely operational documentation, or more simply, the operator's manual of the drone. Using the example of the site with the description of the DJI unmanned aircraft system, it can be argued that is the following trend. The description of various models differs in content even within the conditional group of analysis in terms of the takeoff weight of the unmanned aircraft vehicle. The reason for such difference in the description of characteristics may be the lack of regulation in this matter and different products positioning strategies compared to competitors' analysis. Those characteristics in which this product is inferior to competitors are not indicated, and banal gouging or individualism on the part of specialists responsible for this area By the way, technical writers often work remotely, which is another factor of desynchronization. The consequence of the trend is the loss of information, i.e., to more analysts, even more different conditional groups. By takeoff weight, we analyze the more detailed the table of analysis, and therefore the more and more complex technical requirements and technical assignment will be able to form. The table is no exemption. As you can see, some of the indicators from a number of models are missing, but we will able to fill in their technical requirements gaps for our newly designed product due to the availability of this information for other models. Accordingly, during the fill-in process, the table was supplemented with new lines as the degree of detail of the description of unmanned aircraft systems and units increased until it reached the current state. Generally speaking, the initial description of individual systems looks either insufficient for the information of structural and functional model or absolutely unsystematic. However, in the process of filling in almost every system or unit, a certain logic gradually begins to emerge, the results of which listeners who may be specialists in individual systems or units of unmanned aircraft system will be able to evaluate form from a professional point of view as the following stages analysis. So let's consider the structure of the presented table of analysis. Its structure, as we can see, differs from the typical description of the technical characteristics of a consumer unmanned aircraft vehicle with a weight of 1 kilogram and a price at about 215,000 rubles, which appears to us is a form of a conditional camera taped to an engine with a propeller and a battery. The presented table of analysis in particular consists of several main sections, namely general characteristics of the drone necessary to fill in a corresponding section. See the table in the section basic parameters and characteristics and technical requirements and technical assignment. The next platform features. The next useful load characteristics. The widely used term of payload is not quite appropriate in this case. Is more applicable, for example, to cargo or passengers, and we carry a camera. Characteristics of ground equipment is next. External pilot station or EPS. Thus, all these four listed sections, the drone appears to us as a conventional camera with a propeller. This model is sufficient for the consumer but not for the design engineer. Thus, it's logical to assume that the presented table of analysis, which we plan to use, among other things, for the development of a new drone using reverse engineering and value analysis, should have broader functionality. The first requirement for such a table that comes to mind is its ability to display in the table of analysis of the design structure of the product in the first approximation, which is implemented in this case. Let's consider the structure of the presented table in more detail. In order to establish a clearer parallel with the structural model of the object of analysis, structural model and the structure of technical requirements and technical assignment, according to GOST 15016, which in this case will be performed by us as part of the subsequent stages of analysis. The first platform section includes mechanical part and equipment. The section mechanical part and third includes power plant, fuselage, wing, fuselage or body, wing and tail, landing gear, pylons, and the section equipment includes communication equipment, flight and other storage system, data storage system, navigation equipment, headlights, aerial lights, battery and flight control system, and particular various sensors. The second is this useful lot. Section includes main and additional cameras, camera stabilizer, suspension, and other payloads. And the next section is ground equipment or external pilot system. Includes ground equipment used during flight and short-term ground equipment. or sorry, it's EPS, it's external pilot station, not system. No? The second requirement for table of analytics is the possibility of using the form structural and functional models. As we have already mentioned in the theoretical editions of our course, the basis of the formation of the structural model is initial technical requirements and technical assignment, and as the design engineering documentation is developed, electronic specification and 3D models and a statement of purchase parts can be used as initial data. A detailed table of analytics is formed at the pre-project stage, i.e. at the stage when there are not only 3D models, specification and list of purchase products, but there is also no full-fledged technical assignment. Thus, the presented table is the most general approximation of the design structure that can only be. The third requirement is the possibility of using such a table to generate an option list document used in activities by the marketing service as well and by sales departments. Simply put, this table of analytics should certain a complete list of options which can be later be divided into basic and additional ANS in accordance with the marketing policy of the project and the sales strategy. In fact, this issue is solved by adding a column to the table which will be indicate base or additional. The fourth requirement is related to the functionality of production engineering service, namely the formation of make or buy statement. The solution is similar to the indicated above, and column with the two make or buy options is added. The mentioned characteristics of basis and additional option lists and make buy are placed in the corresponding columns of the table of analytics for the parameters of which they are logically applicable, i.e. those that can be attributed either to basic or additional options depending on the model and pricing strategy of the product based on the information in the columns of the databases or additional option list and make buy. Further separate documents are formed in these areas. In particular, a list of purchased products and list of purchased products approved for use. Let's consider the final block of the analytic table called developed unmanned aircraft system at current milestone pre-project. It differs at the different milestones. As the name of the block indicates, its content will be adjusted and supplemented at intervals corresponding to the transition to a new milestone of the project. In fact, filling in this block is the applied purpose of forming table of analytics, except for the general formation purpose which we discussed above. The general structure of the block to development unmanned aircraft system at current milestone per project is similar to the structure of the classical calculation of internal production, with the following differences due to the use of value analysis and value design engineering methods. The block direct costs for components of the lower level abstraction is an analog of the section material cost of the classical calculation. The block direct costs for components of the upper level abstraction combines the section production costs and overhead costs of the classical calculation of internal production, with the only difference that the material costs associated with the assembly work are added to it, which are otherwise not very significant for a manned aircraft system. In the commercial performance business plan indicators block, marginal profitability is calculated taking into account the planned selling price of a manned aircraft system. So, let's imagine that the entire table, except for the developed unmanned aircraft system block, is filled with data available on open sources in accordance with the business process, the target sales price. In accordance with the business plan, the target sales price of 70,000 rubles is entered in the table, respectively the analog closest in design and composition of the equipment. In this case, we will be MGX Box 7 with a sales price of 15,000 rubles. which is now presented on the screen. The only deviation from the actual design of the closest analog will be that we will add a conditional low budget FPV goggles, and the MGX Buck 7, although in fact isn't there. In order to demonstrate the principle of reverse engineering, it should be noted the introduction to the design of first-person view goggles, which increased the level and convenience of the drone operator while simultaneously causing a negative effect in the form of increase of direct costs, and has such a positive effect as reducing one-time costs for developing an application for Android or iOS. Since telemetry and photo-video records tools, as well as settings, are unlikely to be implemented in our budget control panel, therefore a smartphone or table appears in the unmanned aircraft system, and therefore the development and subsequent maintenance of a specialized application is necessary. If a helmet is included in the unmanned aircraft system, all the above-mentioned user functions are transferred to the FPV helmet interface. In addition, by switching to a helmet or FPV goggles, we are moving away from the video transmission range corresponding to clocked frequencies of Wi-Fi and moving to the freer 5.8 GHz and band with the ability to select frequencies, which in the most cases is not available for low-budget unmanned aircraft system. When working through an Android or iOS application, in general it makes no sense to enter detailed technical specification in the developed unmanned aircraft system block at this milestone of the project, the same form they are presented for the analog. However, data from the option list and make a buy statement relative to the responsibility of the production engineering service, as well as data on direct costs, see block direct costs and milestones, and the commercial indicators see the block commercial performance business plan indicators. At the pre-project stage can already be made, albeit the first approximation. The direct costs of components at the lower level abstraction in the amount of 10,000 870 rubles are calculated as the sum of the cost values for the components of developed unmanned aircraft system in 5 columns. The first, calculation for a component from ERP, internal production. Second, direct costs of the prototype component, prototype technology. Third, price of the purchased products, external supplier. The fourth is export price of the purchased products, export assessment methods, and the last, fifth, is the selling price of the component in retail network. There are 5 columns for the following reason. They provide typical options for estimating the cost of product components for the stage of project documentation, i.e. if you perform the calculation according to the data from the column calculation for a component from the ERP internal production, it means that the component is produced by internal production for our company, and the cost calculation is entered into the ERP system and therefore can unload it and used by a cost engineer if, according to the data from the column direct cost and prototype component or prototype technology, therefore the component is manufactured using prototype or more simply very expensive technology, for example on a 3D printer or completely manually by highly qualified locksmith, and etc. The obvious advantage of the prototype technology is the absence of the need of pre-production, and as a result the short production time of a component. If according to the data from the column price of the purchased products external supplier, then we have a commercial proposal for the purchased products from external supplier formed on the basis of our production volumes and one-time costs, and if according to the data from the column retail selling price of the product component, means that our unmanned aircraft system prototype, which will be manufactured at the pre-design stage, has a component purchased in the retail network and the part of the column price of purchased parts from external supplier or export assessment methods, There are more options for filling this column, starting from the product cost management software and software for the technical benchmarking of the Atomark 1 type, ending with the assessment based on expert calculations. Generally speaking, for the design documented stage, installing components purchased from the retail network on a prototype is normal practice, not only in our case, the unmanned aircraft systems, but also, for example, in this case of new products is the automotive industry, which I personally witness in the course of my work. For the analyzed milestone, value can be entered only for the 5 given columns. An important point when filling the assigning actual costs to function carriers is that we put down the amount of direct costs in the listed 5 columns, only for components of the 4th and 5th levels in our case and lower levels of abstraction in other cases. I.e., if when setting the cost values we accidentally fly out to a higher level, for example for the 3rd or 2nd level, this indirectly indicates the structural model is formed with errors, since as a milestone of the pre-project information about the actual prices of components of the upper level abstraction is extremely unlikely, since the assembly units which should take into account production costs or VAT and overhead costs of domestic production. Thus, settings the values of direct costs for components is a table of analysis not only a stage in the formation of initial data for the formation of the S diagram, but also a necessary stage in verifying the correctness of the structural model and the extended functional basis, or more simply of the technical requirements or technical assignment structure that can be formed based on the result of analytical work. In more detail, the logic of assigning components to certain levels of abstraction, as well as their display on S and RQS and 6S diagrams, will be described in section 7 on the formation of the unmanned aircraft system structural model. We only note that the 4th and 5th levels mentioned above mainly purchase parts, simple parts and catch simple assembly units consisting of from 2 to 5 parts are placed, for which value of direct cost can be taken into account from the commercial proposal or ERP system, and the high levels of abstraction, it means 1st, 2nd and 3rd level of systems and aggregates, i.e. components for which calculation is difficult at early milestones of the project, in our case the pre-project milestones, i.e. the construction of diagrams S and RQS and 6S for higher levels of abstraction. It should be noted that the closest analog of MGX Box 7 a similar logic of adding up the prices of components and obtaining the final value of 15,000 rubles in the column retail selling price of the product component will not work, since the price of the the retail price for the kit will obviously be lower than the sum of prices of component purchased separately from the same retail chain. For MGX Box 7, the retail selling price of the product component field isn't filled for all components, since most of them, except for consumables and most expensive ones, are designed for the entire life cycle, sensors, diodes, and etc., i.e. no one will change them to such a drone because will cost them buying a new drone. In this case, when forming the amount of direct costs for the unmanned aircraft system being developed, we use information from other sources and install alternative components other than those of an analog at the discretion of the design engineering departments of the project team. Direct costs for the components of the upper level abstraction, aggregate systems nodes in the amount of the 2,200 rubles are calculated by the expert method, since such information usually missing for the pre-project milestone, especially in the case of reverse engineering of an object in the design of which is being performed at the first time. Accordingly, the marginal profitability column provides an expert assessment of the marginal profitability of a product at the current milestone of the project, which in this case 23%. I do not undertake to judge whether this is sufficient amount, since conditional sufficiency depends on many factors, including overhead costs, profit margins, including of the business plan, and one-time tooling costs, tooling resources, etc. In general, for some companies it will be sufficient, and for some no. Let's add the following initial data to our case. Our company has its own assembly plant, which allows for the final assembly of this type of unmanned aircraft system, and also has equipment for the manufacture of ABS plastic parts by injection molding and the manufacture of rubber parts by locksmith methods. For example, rubber chassis or rubber landing gear supports, similar to those used to the MGX-7. Let's move from the unmanned aircraft system general characteristics block, which displays top-level product information, to the blocks corresponding to the main units and the system of the unmanned aircraft system in question. Component fuselage in this case is performed like an analog by the methods of injection molding by internal production, thereby achieving the indicates low cost of 118 rubles of the option list. The first approximation and option of basic and additional options can be introduced in the form of manufacturing the fuselage from the ABC plastic or carbon fiber. In the marketing campaign, the carbon fiber option can be positioned as more resistant to mechanical influences and having a more aggressive or sporty appearance or sporty external texture. The total amount of direct costs for the product in this case is formed on the basis of the basic design option, and for additional a separate calculation is formed, the information from which can be used within the framework of the sales model. For example, in the price calculator taking into account the basic and additional options and the unmanned aircraft system dealer's website. In this case, we omit the tail and wing blocks, since they are absent to the design of quadcopter, and move to the landing gear block. The situation regarding the options in this case is similar, since AMS rubber is accordance with name can be positioned as weather resistant and more resistant to abrasion than the TK MSHT rubber. According to the protective arcs and pylon body blocks, the logic of the same with the fuselage. With regard to the power plant, namely propellers and electric motor, the situation is somewhat different. Firstly, because they are purchased products, and secondly, since we managed to get commercial proposal from the supplier on the four propellers, i.e. engines for the prototype, obviously we'll have to buy in the retail network at a price that is in case. Information about the price of this unit of the retail network for the MGX Bug 7 analog was useful to us. The retail price is significantly higher than the price that we could get from a direct supplier of manufacturer having a significant annual production volume, and it's turned out, for example, the case of an air propeller or a propeller. Accordingly, at subsequent milestones, when the procurement service or buyer service find a supplier, engine costs will obviously decrease, allowing to increase the overall marginal profitability of the product. For other components and systems, the feeling logic is similar. Based on the table of analogs, basic graphical analytics can be formed, the content of which depends on the object of analysis. The list of characteristics can be displayed in graphical analytics should display in more important characteristics from the point of view of determining the trend of design changes. For example, if the conditional mechanical parameters of an unmanned aircraft vehicle are considered the most important characteristics, i.e. the value of the payload relative to the takeoff weight of the unmanned aircraft vehicle for the range or flight time relative to the mass of the battery, then these parameters should be included on a graphical analytics. Of course, for the DJI brand camera drawn line with are considering the list of critical parameters that affect not only the values of its production costs, but also the final market price isn't limited to the mechanical parameters listed above, but also includes conditional non-mechanical parameters, such as characteristics of the communication system, navigation equipment, photo and video cameras, flight control system, etc. In the case of value analysis, the construction of graphical analytics for mechanical parameters gives us a certain trend that reflects the dependence of some parameters on other, for example, the dependence of flight range on battery mass, etc. Then the construction of graphical analytics for non-mechanical parameters gives us exclusively a description of the DJI marketing model, which obviously should and will be taken into account as a part of design of the value analysis and value design engineering method. However, it's not interest to the designer to the mechanical part of the unmanned aircraft vehicle from those positions. For example, the camera, this is a payload that must be placed in a given height for a given time and more from point A to point B at a given speed. Next, we will be able to make sure that the value analysis and value design engineering is a universal tool that can be used by both designers of conventional mechanical and non-mechanical parts, as well as designers at the design stage of the project, as well as marketers forming a sales model. So, as an example, let's look at an example of graphical analytics for the following sections. The first, general characteristics of unmanned aircraft system, second, battery pack, and last, remote control and radio equipment. From the resultant graphical dependence, it can be concluded that in terms of the characteristics considered all analytics, except for MGX Buck 7, which is the cheapest, 5 times cheaper than the standard analytics, have approximately similar characteristics. Looking ahead, I will state that the point of introducing MGX Buck 7 to the list of analytics is the presence of an analog based on the analysis of design of which options for reducing direct costs for individual components and more expensive analogs can be considered. In addition, it's in MGX Buck 7 and 2 other lighter devices weighing 135 grams and 74 grams. They were specially purchased and flown with the FPV goggles control, smartphone control and direct control in the field of view by yours truly as part of the consideration of this case. In order to access the practical features of the operation of these small class micro unmanned aircraft vehicles, and the formation of the most correct structural and functional model, as well as an assessment of the degree of satisfaction of quality of performance and consumer functions, which will be considered by us at the next stages of the analysis. Thus, the list of analytics for reverse engineering has been formed and verified as a first approximation, and therefore can be used as the next stages of analysis. The results of completing step 4 is formation of the initial data for performing analytics within the framework of reverse engineering of unmanned aircraft systems. And the second, identification to harmful deviation and the characteristics of analytics and the exclusion of the error introduced by them into the average values of unmanned aircraft systems and the characteristics by estimating the value of the standard deviation. Stage 5. At the fifth stage of the analysis, data verification is performed in the mass column of the analytical quantities block of the analog table by the weight list is formed on its basis. Weight list or weight sheet. It should immediately be noted that in the full version of the weight list for the unmanned aircraft system, ground equipment will be present. More precisely, a separate list will be created for the ground equipment, either in a similar or simplified format compares to unmanned aircraft vehicles. In our example, we will consider the formation of wait lists only for unmanned aircraft vehicle, or without wait list, or without external pilot station. From the point of view of regulatory documentation, when forming a partition scheme for the unmanned aircraft vehicle wait list of the quadcopter scheme, in my opinion, the partitioning scheme given in the standard OST 02565 helicopters can be taken as a basis as a further approximation and classification of masses, and the corresponding standard OST 1 02564 characteristics of helicopter masses, terms and definitions. In the case of consideration of the aircraft type, unmanned aircraft vehicles, the relevant content standards is OST 00434 passenger aircraft classification of masses, and OST 00428 weight characteristics of the aircraft, terms and definition. The listed OST are synchronized. The listed standards, for example, are synchronized with each other, which is confirmed by the presence of the reference to the OST 00428 and OST 02564. Anyway, OST 02565, judging by the ear, was developed later and contains a more visual, in my opinion, graphical scheme of mass classification. Therefore, for initial acquaintance, I recommend starting with a standard and not with an airplane one in which there are no graphical flowcharts but only text and a table. The listed normative documents would be extremely useful to those who do not have a ready-made table of analytics and preliminary scheme of structural and functional division. Given in the column initial data for structural and top-level functional model, for us in this case it will only be enough to check for absence for obvious logical contradictions between our scheme of structural and functional division and the scheme given in OST 02565. If the listener takes the trouble to familiarize himself with the mentioned standard, he will be able to see that there are no logical contradictions in the schemes. Therefore, we proceed directly to the formation of the wait list. So, the data for the wait list can be generated in following ways: application of statistical weight formulas, engineering methods of weight estimation. The second, determination of the weight of aggregates by disassembling them, followed by measurements and weighting. And the third, determination of the names of purchased products, electric motors, propellers, and etc., in order to obtain their description of the developer's website. With regard to the first method, the most obvious example is widely used formula for the statistical determination of the payload of unmanned aircraft vehicles. We are talking about a statistical ratio according to which the payload mass is about 0.22 to 0.27 on the takeoff weight. An example of the approximation of statistical formulas is the formation of the initial ounce for the formation of technical requirements or technical assignment, and subsequent value analysis and design engineering is the determination of the payload mass in a block of columns, mass and columns absolutely and relative, included on it containing absolute and relative mass values respectively. A simpler example to determine the mass of the camera stabilizer cover finding the difference in takeoff masses with stabilizer cover and without stabilizer cover. It should be noted that there is a statistical formulas in the educational and methodological as well as scientific literature for calculating the mass of individual units and systems of airplanes and helicopters. However, their use, in my opinion, is too rough and approximation. Firstly, due to the difference in the number of corresponds already mentioned above, which can be several orders of magnitude. Secondly, the formulas for human-controlled devices take into account the life support systems and units and accommodation of the crew and passengers. And thirdly, the strength standards, in particular the reserve coefficients used for manned and unmanned aircraft systems, differ. With regard to the second and the third methods, it's logical to note their complexity, i.e. the needs for access to a physical sample, as well as the availability of special equipment. In the automotive industry, there are examples of specialized software for reverse engineering, for example, Atomac 1, in which you can get acquainted with the results of qualified disassembly of measurements, weighting and photographing, but I personally do not know about the availability of such publicly available commercial software in the field of unmanned aircraft system. Sometimes video reviews of unmanned aircraft system disassemblies or analysis of their components after unsuccessful piloting appear to the public domain. Respectively, for some components, data on the manufacturer's name and characteristics can be obtained for subsequent search of data on the unmanned aircraft system and their characteristics on manufacturer's website. The general structure of the wait list used in the pre-design phase of reverse engineering is relatively simple. The table is divided into three conditional zones indicated by green, yellow and red colors. The green zone on the table shows the actual mass values of the components of the unmanned aircraft vehicle analytics, which can be obtained in the following ways: by analyzing the description of unmanned aircraft vehicle analytic components specification on the developer's website, by weighting accounting according to the results of the analysis, by using specialized software for technical benchmarking available for selected branches of engineering, and other options for obtaining information. Okay, the next yellow zone of the table shows an expert assessment of the mass of the upper level structure components of the unmanned aircraft vehicle, formed using engineering methods, in particular the use of statistical formulas to calculate the mass of the unmanned aircraft vehicle. And the red zone of the table shows the values determined by subtracting the actual and the expert values from the basic unmanned aircraft vehicle mass index, named as the pre-flight mass. In fact, we are talking about a conditional black box of mass values that need to be distributed in accordance with the structure specified in the table of analytics. In the process of clarifying weight list, weight sheet, when moving from the pre-project milestone to subsequent project milestones. The first feature that we can see in our waitlist form, working with fork values of the mean and max, until the moment when the value is obtained using the above mentioned statistical weight formulas, engineering methods for estimating mass, are used in the waitlist. Of all the analysts shown in the table, we are able to perform dismantling and weighting of structural elements only for MGX Box 7. Therefore, for the rest of the analytics, we can use only statistical methods of mass estimation, namely the fact that the most unmanned aircraft vehicles, the payload is about 0.22 to 0.27 of the takeoff flight. The logic of the transition from yellow to green is simple and is embodied of the principle of forming a weight list, according to which actual value of the formation of a weight sheet prevails over the value obtained using statistical weight formulas. In particular, as soon as at least one actual mass value appears in the useful load section, we immediately proceed to work with the actual values to transform the conditional delta to the undistributed weight section of the weight list. According to the platform section of the weight list, this principle is implemented for all analytics, since for all it was possible to find the actual mass only for the battery and the useful load section. We have information to switch the actual values only for MGX Box 7 for the reasons outlined above. If we try to formulate the principle of further filling in the fact clarifying the weight list, then it actually consists in bringing the mass value indicated in the column undistributed mass to zero, i.e. forming a complete mass distribution for the degree of abstraction adopted in the table of analytics. Although this degree of abstraction is insufficient for the formation of design documentation, it's sufficient for the project milestones we are considering and rather on pre-project stage. Another reason why it's necessary to strive to move as quickly as possible from the statistical values of the weight list to the actual ones is the presence of deviation for small class micro unmanned aircraft vehicles from the statistical weight values for the larger devices, which becomes obvious not only in comparison with larger unmanned aircraft vehicles, but even within these groups of UAS, in particular our sample of analytics. As we could already observe in the framework of the analysis of graphical analytics, the MGX BUG7 analog has some deviation, which we attributed to its cheapness and possibility of being classified as a transitional class between amateur quadcopters and conventional toys. In fact, the analysis of the MGX BUG7 weight list is the payload list or useful load list, of which includes only a camera, a plastic non-mechanized suspension. In this case allows to assert that the application of statistical weight formulas in relation to small micro IOFs is incorrect. If we had the opportunity to weigh the individual components to other analytics, it's highly likely that we would find deviations from the statistical weight formulas for the payload. In addition, the reason for deviations from statistical weight formulas for a new generation of UFs may be changes the applied technological processes, reduction of processor thicknesses during injection molding. The second, changes in the list of used structural materials. Third, change in the strength standards and the safety requirements for UFs flights. And the last, changes in environmental standards and etc. In the case of the airplane or helicopter of the classical scheme, for the alignment calculation is relatively simple and has the following order. For each name of the component mass, a coordinate is determined for the general coordinate system of the aircraft. As a rule, all coordinates are xy's with a minus, since a coordinate system is located at the extreme point of the nose cone. Further, based on these coordinates, the total moment is calculated relative to the central data center, located, for example, of 23% of middle aerodynamical chord of the aircraft, or relative to the point of the conditional suspension of the helicopter, located on the area of intersection of the axis of rotation of the main rotor and the conditional plane of its rotation. In the case of quadcopter, the suspension scheme of the device may, in first approximation, be simplified to a beam. A beam in this case is a fuselage or body, suspended on two high hinged supports. Each support is a matching projection of electronic motors located on different sides of the plane of symmetry of the quadcopter. Thus, if we have two hypothetical components of mass M1 and M2 applied to the points of a beam fixed on hinged supports, then we have nothing more than a classic problem of resistance of materials, which some more of an engineered specialty has the good fortune to encounter. Next, we make up to the equation of the total moment for each of the supports with one unknown. Based on the results of solving this equation, we can select an air propeller and electric motor for the unmanned aircraft vehicles that meets the loading condition. Generally speaking, this example demonstrates a number of reasons why quadcopters have become the most common UFs. In particular, the first reason of the simplicity of calculating the load of the propeller. The scheme shown in this sketch, generally speaking, is nothing more than a centering calculation scheme for helicopters of the longitudinal scheme, such as Chinook, CH-47, Sikorsky CH-54, Boeing Vertol CH-46, C-Knight, and Yak-26. I will not delve into the problems of creating these helicopters and set out the popular science literature, mentioning only that special mechanical vibration absorption devices with a sufficiently large mass are installed on Chinook CH-47. The loads acting on the fuselage in the case of full-size machines probably also created certain problems. However, in the case of small class micro UAS, the fuselage of which can be called thin-walled load-bearing structure with a very large stretch, this problem can be ignored. The main problems of, in this case, flight control system, because in two screw drones of a longitudinal or transverse scheme, like a MIL V12 machine, it would inevitably have to create a skew machine and other elements that negate many, including the economic advantages of the drone. Therefore, quadcopter circuit that combines such advantages as simplicity of the design of the fuselage and pylons and beams, ease of calculating the alignment and section of electric motors with screws, coupled with a relatively simple flight control system by changing the speed of rotation of propellers. It's most technically and economically efficient as suited layout scheme, which is the key to widespread use. With regard to hectocopters, octocopters, and other UAVs with even more rotors, the alignment calculation scheme, oddly enough, is even more simplified because the more electric motors were installed on the so-called wheelbase, the more the calculation models begins to resemble and distributed load applied to a conditional closer secular, a frame connected to the center of the circle by pylons beams, i.e. we simply estimate the mass of the payload. The mass of the fuselage, the pylons of the systems and the power plant and place load application center is the center of the frame, and select screws and electric motors based on its information. If the helicopter is positioned symmetrical relative to the plane of symmetry and its electric motors are projected into conditional frame points, which are hinge points of support in our scheme, then we obviously get different loading at these points from the payload and fuselage, i.e. from the point of view economy. We should choose two types of engines and two types of props. However, I have not encountered this even in cargo, mutual, domestic and foreign drones that can be adapted to a given payload, i.e. even in them all the rotors are the same. So, based on the calculations described above, it can be argued for the quadcopter as well as helicopter and airplanes of the classical scheme. Design engineering scheme can be simplified in the form of beam placed on two pivoted immovable supports. We do not consider the issue of longitudinal and transverse stability in this case, although it's also important, since any change in the direction of movement of quadcopter is usually accompanied by the change in pitch, roll and yaw angles, which is unfavorable vectors, firstly when shooting video and secondly when controlling drone in the confined space scenes, in the moment of the non-floating start and the drone's position change in space. The pilot on FPV drone loses orientation in space for a short period of time and may encounter an obstacle. In case of a change of the yaw angle, the quadcopter doesn't have such problems. Within the framework of this case, we will not add numerical values to the mentioned columns, since this requirements in depth study of the fuselage design, evaluation of the mass of aggregates, etc. Let's just keep in mind that the subsequent milestones of the unmanned aircraft vehicles reverse engineering project, weight team or a similar unit from the organizational structure of the design bureau will be responsible for filling in. Based on all of the above, let's try to formulate the purpose of forming a weight list of analytics. Based on the list of analytics, mass values of the main units of the platform and payload should be obtained, taking into account harmful deviation, non-standard increased mass on the MGX by 7 platform, non-standard increased battery capacity of Xiaomi FunSnap Diva 2 SE, etc. Masses arising as a process of analyzing a sample of analytics of small class micro UAS. Method to identify and avoid the influence of harmful statistical deviations. The first method, visual tabular representation, see tabular weight list of analytics. The second method, visual graphical representation, see graphical analytics, generated based on results of filling in the table of analytics. And the third method, use in addition to calculating the arithmetic mean, average hospital temperature, the calculation of the standard deviation, see my book, the calculation of standard deviation. Okay. I suggest not to delve into the theoretical description of the advantages of using the standard deviation value over the arithmetic mean value, which is the most often used in practice when processing first approximation data, nothing only the essence. Even single deviation of significant magnitude has significantly affected the value of the arithmetic mean. Simply put, if one of the experts went crazy shortly before the survey and set the value 1 on a 10 scale, when the remaining 9 set values from 8 to 10, then he thereby shifts the value of the arithmetic mean, forming a so-called average temperature of the hospital, in which we will obviously have to spend some time in the future. If you assume that before the survey an additional two crazy person that was a man who quarreled with his wife, and the result of which he was out of sorts and also, like the first gentleman, unreasonably slapped one, then we gave an even greater shift of the value of the arithmetic mean, and accordingly on incorrect result of processing statistical data. The experience of data processing within the framework of value analysis and design shows that the optimal method and term convenience and accuracy for determining the correct average value is the described content is the calculation of the standard deviation. So, in our case, we are not dealing with the results of survey of experts, which, by the way, we will analyze further at the stage devoted to the degree of satisfaction and the quality of the implementation of functions, but with a sample of analytics developed by unmanned aircraft system. In accordance with the methods of from 1 to 3 listed above, which allow to identify and avoid the influence of harmful statistical deviations, we can analyze two groups of data. First group, the results of the analytical and technical characteristics compliant in a tabular form of the graphical analytics tab, on the basis of which the diagrams we'll have already considered were built. And the second group is the results of the formation of the weights list of analytics. In the developed unmanned aircraft system section, the weight list contains average values of weight indicators by analytics, which in the first approximation allow us to estimate the target values of the weight indicators for the unmanned aircraft vehicle being developed. As I mentioned above, in the case of using arithmetic averages, it's possible to set incorrect target weight values associated with a harmful deviation of non-standard deviation. The standard deviation block can be used to verify the permissible range of max and mean values of the target mass. Let's consider an example of checking the obtained average values by analytics. Using information about the standard deviation, the only component for which there is an actual weight data for analytics in this case is a battery. The weight data obtained as a result of weighting in this case is available only for MGX box 7. If you had access to physical samples of other analytics, then we could consider using the standard deviation for a larger list of platform components and payload. So the range of average, mean and max, absolute and relative values of battery weight is from 85 to 92 grams and from 34 to 37% respectively. The standard deviation from the mean and max absolute values is 17 and 10 grams. Therefore, there is a battery mass of unmanned aircraft vehicle under development, developed as a result of the design, can be in the range from 68 to 103 grams. In the first approximation, this will be considered normal. This is one is used in development, for example, in case of problems with alignment, i.e. we can allow a decrease or increase in the mass of the battery in this range, and at the same time we will remain within the standard deviation for relative values and the corresponding range from 0.27 to 0.41. Following a similar calculation logic, we can determine the range of permissible mass within the standard deviation for any structural element of unmanned aircraft vehicle being developed. Let's go back to calculating the standard deviation for the graphical analytics step. The calculation logic in this case is similar, except that we do not use min and max values, which has become simplification. However, it's quite acceptable for the milestones of the pre-project. Okay, the result of completing step 5 is the formation of a base for filling out the unmanned aircraft system weight sheet at subsequent milestones of the project, in particular calculating the alignment of the unmanned aircraft vehicles being developed as part of the unmanned aircraft system, as well as evaluating the operational characteristics of unmanned aircraft systems ground equipment. Stage 6. As part of the sixth stage, based on information from the table of analytics, we presented on the screen a combined format of the list of purchased products, which includes information from two formats of lists of purchased products listed in a GOST R2.106, namely list of purchased products, see format 5 and format 5A in Appendix A of the standard, and the list of permits of the use of purchased products, see format 6 and format 6A Appendix to the standard. The work performed at the fifth stage should not confuse with the formation of the BOM of the bill of material for the products being developed, i.e. in fact the first estimate of the structure of the unmanned aircraft system being developed, provided that its components are manufactured primarily using prototype technologies, 3D printer, manual locksmith work, stamping and prototype tooling with a small, for example, silicon casting, vacuum infusion, manual laying out and the molding of composite parts, etc. The minimum list of consumers of information provided in the combined format of the list of purchased products as part of the implementation of subsequent milestones of the project includes the first, the design engineering department responsible for the formation of purchased products list based on data from the design documentation, and the buyers or commercial department and cost engineering department. The formation begins with the re-verification of technical and economic data in the sectors or sections of the table of analytics containing purchased products, in particular the information of the actual values column of the analytic table is verified, since the information from this column will be used in the combined format of the list of purchased products. Verification of the information in the column price of purchased parts, the block analytical quantities, where reference prices for individual components obtained from the open sources are given, is not mandatory, since in the case of forming the cost structure of the unmanned aircraft vehicle being developed based on these references prices, the final price of the entire product will be limited to correct, i.e. correct exclusively for the prototype assembly stage. The purchased products for which will be conditionally purchased in retail at prices obviously higher than the prices according to the specification in the case of supply contract. I do not think that the form of the list of purchased products requires an extended comment, since as many repeats the format given in GHOST are 2.106, we will not only the following nuances related to the revision of the table and the unification of the format of the list of purchased products and the format of the list of permits for the use of purchased products in a single format. The basic option in the applicability status column refers to the purchased products which is considered by design and engineering department as the most suitable for use in the designs of the unmanned aircraft system being developed. The alternative option in the applicability status column means purchased products with characteristics close to those required, the use of which the design of the unmanned aircraft system being developed is possible if there is no access to purchase for the basic option. Fill in the columns organization that issues the permit and the column number and date of the permit protocol is performed in accordance with the instructions and protocol formats given in GHOST 2.128 of United System of Design Documentation Procedure for use of purchased products. Fill in the note column, as I mentioned above, is preferred either the basis of data from the actual values of the table of analytics column or on the basis of information from the other resources, the website of the developer of the purchased products, exhibition materials, and etc. The results of performance step 6 is formation of a combined format of the list of purchased products as the first approximation in the basic and alternative format, i.e. indicating the main variant of the purchased products that is planned to be used in the design of the developed unmanned aircraft system, and alternative options offered either on the basis of information complied in the table of analytics component of unmanned aircraft system analytics or independently about it. And the second, the formation of a database for filling in the list of purchased products, see Format 5 and 5A Appendix A, and the list of permits for use of purchased products, see Format 6 and 6A Appendix A of the standard, as the path of the development of the design documentation and subsequent milestones of the project. Stage 7. As a stage 7 devoted to the formation of a structural model, we closely approach the direct value analysis, which begins with answering the questions: what is the primary for the considered case, a structural model or a functional model? Since the case sounds like reverse engineering, i.e. reproducing an existing piece of equipment without directly copying it, we can say that the procedure will still be closer to the opinion with a ready-made structural model, which in fact has already been formed by us in blocks, in the next 3 blocks. Platform, second, useful load, and third, ground equipment. With regard to the general characteristics of unmanned aircraft system blocks, the table of analytics should be noted that it will also be used in the future, i.e. It's not useless. All data from the general characteristics of the unmanned aircraft vehicle block will subsequently be included to the standard technical requirements and technical assignment section according to GHOST 15016 under the title Basic Parameters and Characteristic Properties. Generally speaking, in the modern world it's quite rare for something to be created that has no analytics, i.e. when it comes to the case, a pure engineering transition in the understanding of this term introduces by us in the issue number 11, Engineering Transition, Significant Assessment Methods for Functions and Their Carriers, of our training course. When a functional model is created and based on it, a completely new and paralleled structural model consisting of physical media is created. In short, in the form of general initial data, the case is described in sufficient detail, and in Form 1, the goal and limitations are formulated, namely, reduction of the technical and economic characteristics of the value model of the developed unmanned aircraft system by no more than 5% relative to the average value for analytics. Thus, since it's not indicated anywhere that we should design of unmanned aircraft system with a significant degree of novelty, which no one in the world has ever designed, then with a clear consequence we can use the three blocks of the table listed by us is to form the first approximation of the structural model and further form the first approximation of the functional model based on its functional model of an UAS being developed. Let's evaluate the degree of abstraction required in this case in accordance with the table of degrees of abstraction which we discussed on issue number 7 of the cost engineering training course. So, it's obvious that in our case the degree of abstraction is a product as a whole, and the basis for the formation will be the above mentioned blocks, platform, useful load and ground equipment. In this practical case, we are slightly modified format of the basic and extended structural models, similar to the one we discussed in issue number 8 and 10. Let me remind you that the concept of the main or indivisible care of function, it was formulated by us in the issue number 7 of the theoretical course, by analogy with the concept of the main function used in classical value analysis, so I will not dwell on it. As we can see, the volume of initial data generation by us at the first 6 stages of the analysis is sufficient to fill in only part of the fields of the basic and extended structural model form. There are dashes in the other fields. This situation is normal because firstly, there is a lack of information on the pre-project stage, since in fact we operate only with data from the business plan, as well as information found by us in open sources. Secondly, the format of the structural model is universal, i.e. it's used both on upper and lower levels of abstraction, in particular fields related to mass, description of the workpiece and technological process are usually filled in when analyzing individual parts or small assembly units. In video number 8 of the theoretical course, where the bicycle assembly and its aggregates parts were specifically considered as an object of analysis, the situation with filling the fields of the extended functional model is simpler, since it's much easier for bicycle components to determine the length of the life cycle, determine the probable structural material and manufactured process in the case of unmanned aircraft system. The technical information required for the analysis is presented in a much more modest volume. In this case, all the information that we have based on the results of passing 6 stages has been entered, and the level of abstraction of consideration, as mentioned earlier, is the highest, i.e. in fact we consider the unmanned aircraft system as the level of formation of technical requirements and subsequent formation of their basis of technical assignment. Consider the process filling of the base structural model, highlighted on beige on the screen. We take the information for filling the columns abstraction levels and full name of the column designation of the functions carrier from the table of analysis, and for other columns ordinal name, abbreviation and number pieces. Columns are filled in as part of the formation of the structural model for the first time. The numbering of the ordinal name column, as we can see, is the end-to-end for the entire product, and it's not tied to the abstraction level at which the component is located. At first glance, this approach may seem somewhat clumsy, but experience showed the more complex notation system tied to abstraction levels is less convenient, more time-consuming, and leads to errors, especially when the analysis is performed in a tabular editor manner. In the case of automated calculations, i.e. the system of ordinal designation can be modified to create specialized analytical software for reverse engineering using VA and value design engineering methods. Information for filling in the column block a list of items of production cost and strategic level. In particular, columns contain information on the availability of cost related to R&D, tools manufacturing, payment of royalties, or purchased products, the localization cost can be obtained from design departments and production engineering departments. Let me remind you that the list of purchased and independently manufactured products, the make or buy list, as well as the list of basic and additional options and option list were formed by us as a stage 4 and presented in the corresponding columns of the analytic table and formalized in the form a list of purchased products and a list of permits to the use of purchased products as a stage 6. Respectively, when forming the text part of technical requirements and technical assignment, it will be indicated based on the context of the option list column. It will be indicated that the option belongs to the basic or additional ANS. In addition, an appendix of the technical requirements and technical assignment will be formed with a list of additional options, which is also formed on the basis of the option list column of the table of analytics filled in by us at the stage 4. The column R&D, tooling and royalties are additionally divided into the columns basic options and additional options in order to make the assessment of current one-time costs at the milestone more accurate. Information about basic and additional options was previously entered by us in the column option list of the table of analytics. Let's consider the process of filling the extended structural model, highlighted on the screen in the purple. The extended structural model consists of two blocks of columns, namely a block of commercial data at the strategic level and the commercial data on the local level. We can take the data for filling the columns of the block of commercial data on strategic level on the structural model from the general data block of the table of analytics, the filling of which was considered by us as part of the first stage of the analysis, as well as similar approach applied when filling of the basic structural model requests from the design departments and the production engineering department. In this block, we indicate as the first approximation the volume of production of certain components, for example, on the basis of whether they belong to consumables, see the line propulsor and the component propeller with a life cycle of 0.2 years, unlike other components with a life cycle of 2 years, etc. R&D and the tooling costs for the pre-project stage can hardly be estimated for individual components. Therefore, they are shown in one digit. However, as after moving to the subsequent milestones and receiving a commercial proposal, this section of the extended structural model will be clarified and become more detailed. Duplication of information in the structural model and the table of analytics aims to compose information in a format more convenient for preparing analytics, including RQS and 6S reports, for the case of analyzing individual product components at lower levels of abstraction, i.e., reducing the inconvenience for most users format of the table of analytics to the format of a structural model in relation to the block local level commercial data of the extended structural model. The name, content, and logic of filling in columns are similar to the columns of the block direct cost components of the lower level abstraction of the analytic table, i.e., the data for the filling is taken from it. The individual position taken from the table of analytics will need to be combined, since even in the case of the upper level abstraction of consideration is still less general than the extended structural model. For example, in our case, such positions at auxiliary LEDs and front status indicator should be combined into single of the aeronautical lights equipment position. A similar situation with the combination of several positions into called navigation equipment. In this case, the block commercial data at the local level of the standard structural model is filled, as we see, exclusively with data on purchase components and details of external production components of 4 or 5 levels of abstraction, respectively. When moving the subsequent milestones of the project, the block commercial data at the local level will be supplemented with the direct costs for components or higher levels of abstraction, levels from 1 to 3, as information becomes available on the ERP system. Let's describe the construction of S diagrams based on the structural model. As I already mentioned in the description of the fourth stage of the analysis, the amount of direct costs in the direct product costs block of the tables of analytics, and accordingly in the local level commercial data block of extended structural model we put down only for components of the fourth and fifth levels in our case, and lower levels of abstractions in other cases. I.e., if we starting the cost values, we accidentally fly out to a higher level. For example, to the third and the second, this indirectly indicates that our structural model is formed with errors, since the milestones of the pre-project information about the actual prices of components of the upper levels of abstraction is extremely unlikely, since the assembly units in which should take into account production costs, wage fund, overhead costs, and domestic production. Thus, setting the values of direct costs for components in the table of analytics isn't only a stage of formation of initial data for the formation in the S diagram, but also a necessary stage is verifying and correctness of the structural model and the extended functional basis, or more simply, the technical requirements and technical assignment structure that can be formed based on the results of analytical work. Based on the above, it's obvious that S diagrams can be formed for abstraction levels above the fourth and fifth levels in our case, i.e. for levels from first to third. In this case, components in only one level be displayed on the diagram and either fourth or fifth. Thus, we come to the possibility of formulating the basic rule for constructing diagrams S and RQS and 6S, which may seem obvious to someone, but nevertheless should be formulated, since all components are displayed simultaneously in the local level commercial data block of the extended structural model, and theoretically it may turn out to be so that components of different levels can be included in the diagram and duplication will occur. Before we formulate the basic rule of constructing diagrams S and RQS and 6S, let's return to the thesis we voiced as part of the description of the stage 4 of the case, namely the conclusion that at the fourth and fifth levels, there are mainly purchase parts and simply assembly units consisting of 2, 5 or 10 details parts, for which the value of direct cost can be taken from the commercial proposal of ERP system, and the higher levels of abstraction, levels from 1 to 3 systems and aggregates, are already placed, i.e. components for which calculation is at early milestones of the project, in our case the milestones of pre-project, i.e. it's difficult to build S and RQS diagrams for higher levels, i.e. 1, 2 and third abstraction as a pre-project milestone. So, the basic rule of constructing diagrams S and RQS and 6S in a tabular editor, there are first, when constructing a component cost diagram at single or common abstraction level, primary diagrams should be used. The second, when constructing a cost diagram for components of 2 levels of abstraction, secondary diagrams should be used. As a rule, there is no need to build diagrams for 3 or more levels of abstraction, since diagrams are the most in-demand tools for management, whose representatives do not need to dive several levels down. In other words, details and fastness management is usually not interested. The very definition of primary and secondary may sound different depending on which tabular you use. For example, in the one I use, such diagrams are called primary and secondary. So, since as a pre-project milestone we have information about costs only for individual purchase products made by the prototype method, individual simple parts and components purchased in the retail network, that is, in fact, we are not talking about the direct product costs, but about the distribution of direct costs for component of the lower level abstraction, purchase products, details, fastness, and etc. Then the diagrams S on the milestone pre-project should be named accordingly. For example, flight controller flight controller, a diagram on the distribution of direct costs for local level components. Accordingly, at the subsequent milestones of the project, when information for higher level assembly units becomes available, the name of the diagram will have a wording already more familiar to the ear of the cost engineer. For example, flight controller direct cost allocation diagram. The construction of a primary diagram, a diagram in which the cost of component is roughly represented as the cost of purchased products, excluding production cost for its manufacture. For a level 3 component, flight controller, which includes 5 purchased products of the first level, isn't of particular interest from the point of view of visualization extended structural model. Therefore, we will assume that all subsequent milestones we have information, namely the calculation of direct costs for the manufacture of the flight controller component and direct costs became available. According to it, they amount to 2,189 rubles. Then, if we subtract 1,752 rubles from this amount of the price of purchased products, and let's assume that the material cost of manufacturing a flight controller are so small that they can be ignored, then we get the amount of production cost and overhead equal to 437 rubles. Let's proceed the direct construction of a secondary or two-level diagram on the flight controller component. I will not go into the specifics of building and configuring secondary diagrams in a tabular editor. Nothing in this case, only the following. Firstly, we have two types of S-diagrams, namely a diagram for the pre-project and the first stages of the design documentation, and a diagram for the final stages of the design documentation and the stage of serial design documentation. Secondly, the distribution of direct cost obtained at the pre-project milestone and the conditional subsequent milestones differs in this example by 20%, which is quite consistent with real practice and shows that the direct cost targets formed at the pre-project stage can be significantly adjusted based on the result of the transition to the next milestones, which once again proves the neat design support by the cost engineering department integrated in the structure of design engineering department, the concept of which was outlined in issue number 2 of our theoretical course. The results of completing step 7 is: first, forming the first approximation of the design structure being developed by the unmanned aircraft system in the form of structural model, according to which the table of contents of the table technical requirements and assignment will be formed. And the second, formation of an extended structural model for unmanned aircraft system, including the blocks commercial data of the strategic level and the block commercial data of the local level, as well as the formation of graphical analytics diagram sets based on section commercial data of the local level for the levels of abstraction reflected in the structural model. Stage 8. The format of the functional model. By analogy with the structural model, will also be basic, not extended, but not only because of the lack of commercial information, but mainly for the reasons that I mentioned in the theoretical part of the course. See issue number 11, Engineering Transition Significance Assessing Methods for the Functions and their Carriers. In particular, we are talking about the limitation of the applicability of value analysis, namely the impossibility of its application conditional and immutable systems. For example, the structural model of formed stage 7 has no 3 elements of the first level. There are also 7 elements of the second level. All these elements are assembly units or purchased products, and their exclusion from the design leads to a loss of operability of the object of analysis, i.e. they cannot be excluded. It's precisely such groups that we call conditionally unchangeable, and for these groups it's impossible to apply value analysis methodology to build RQS and 6S diagrams, and it is also ineffective to apply the method of factory search, or MFR, to them. If we consider a small assembly unit, for example, the body of a pylon beam, then it is much easier to divide into function carriers, structural function carriers, which includes a structural model, and form a functional model. It also has elements that can be excluded or added, for example, surface embossing, protective coatings, material thickness, etc. That is, this component is conditionally changeable, and the application of the value analysis and value design engineering and the MFR are effective as possible with respect to this local component, which obviously confirms the design nature of the value analysis and value design engineering. Example of the use of structural and functional model formation indicating the values of significance, relevance, as well as the quantity or implementation of quality of implementation functions. This calculated on the basis of the degree of satisfaction of the upper, middle, and local lower levels of abstraction, using the example of bicycle, which we previously discussed in varying degrees in retail and theoretical issues on 8, 9, and 10 and 11, as was an examples of the constructions of RQS and 6S diagrams. In issues 10 and 11 for the middle of the upper levels were given to clearly demonstrate the capabilities of the value analysis and value design engineering methodology. In fact, as I have already indicated above, the value analysis and value design engineering is used to manage products costs precisely at the local level of smart assembly units and individual parts. The question logically arises. Where is the limit of applicability of RQS and 6S diagrams, or in other words, at what level of abstraction of consideration is the construction of RQS and 6S diagrams correct? The answer to this question becomes obvious when considering the definition of significance and relevance, as well as the graphical visualization of the significance relevance, or R small or big R flowchart, which we discussed in issue number 11 of the theoretical course Cost Engineering. So, the numerical value of the relative relevance of the R function is calculation. R function, its relevance function, is calculated as a product of its relevance significance and the relative relevance of the higher functions, including the main one. In the case of an engineering transition, i.e. the replacement of the high-level functions with physical media or physical carrier, the calculation scheme doesn't charge. Accordingly, if we have no significance value of the calculation chain for the at least one function or function carrier, then determining the significance value and therefore constructing of the RQS and 6S diagram turns out to be impossible. In simple words, this means that if we choose as an object of analysis a large assembly unit, tank, ship, aircraft, etc., with hundreds or thousands of customer functions, then it's extremely like that. Firstly, we will do not able to formulate all the functions even one level below the main functions without delving into a design, only on the basis of expert assessment, or even with a really ready-made technical assignment, since it reflects only top-level functions. Secondly, even imagine that we formulate them, then the application of existing methods for assessing the significance, assessing the degree of satisfaction and the quality of implementation of consumer functions will be extremely time-consuming and will first require significant labor and time costs for completing surveys and then processing the results obtained. We conclude that the boundary condition for the correctness of the construction of the RQS and 6S diagram at the n level of the possibility as complete and correct satisfying the requirements for the accuracy of the analysis results and the possibility of applying significance determination techniques assignment of significance to all functions and carrier at the lower levels of abstraction starting from the n-1 level. i.e. applicability, this includes the methods for determining the significance of m from m1 to m20 announced in issue number 11. Thus, we get an addition to the thesis about the need for system variability, in accordance with the boundary condition for the application of methods for determining the significance from m1 to m20 is a condition for the admissibility of the exclusion of some functions from the structural and functional model. A simple example of immutability, it's impossible to exclude wheels from the machine structure, but from the car structure, but the possibility of excluding moldings. That is, if we choose for analysis, for example, the pylon body, a beam, of a drone consisting of two plastic parts, a swivel sleeve and fasteners, it's obvious that for n-1 level, i.e. for the level at which there will be 4 carriers of functions, we consider fasteners as one carrier. We have the opportunity to formulate all functions in accordance with the classification of functions and constraints discussed by us in issue number 7 of the theoretical course. If we increase the abstraction level to pylons beams, i.e. we will include all structural and functional models, also an assembly unit protective arcs consisting of 2 plastic parts. Then the tabular structural and functional model will increase in size and become somewhat inconvenient to use since they will consist of several dozen lines. However, it will still be possible to build a correct RQS and 6S diagram. Then, in the case of raising to the frame level, i.e. including elements such as landing gear in the analytical model, tail, wing, and fuselage, being an analyst, I would no longer undertake such analysis, because working in a tabular editor with a structural and functional model consists of hundreds of lines is problematic. That determines the degree of satisfaction and quality of implementation of functions will also be very voluminous. In the case of setting the task of performing analysis of body level with not automated analytics, i.e. using a tabular editor by specialists or analysts, the task should be divided into several subtasks that will be solved separately. At the same time, the subsequent unification of the obtained data and analytical reports into a common structural and functional model is impossible, since during the calculation the significance and relevance of the upper-level elements, pylon body, protective arcs, landing gear, and etc. was assumed to be equal to 1, i.e. each of these elements was considered as a conditional separate product, i.e. The point in this case isn't automating the process of working big data, but in the logic of the analysis methodology. Therefore, one of the disadvantages of the value analysis and value design engineering is that within the framework of this methodology it is impossible to obtain analytics of the entire product, i.e. a general RQS and 6S diagram, but is possible to obtain analytics for individual assembly units. In the value analysis and value design engineering methodology, we consider each component of a product as a conditional separate product. Value analysis and value design engineering method is a method that provides local cost management of a product, but not end-to-end and integral method. The limitations of the applicability of value analysis and value design engineering can be classified and divided into 2 groups. First, restrictions at the strategic level and restrictions at the local level. The first, strategic or management level. Value analysis, value design engineering can be attributed to indirect management tools for strategic management of production cost. If it used in design support, within the framework of the activities of the headquarters units of management accounting, through which the following functions can be implemented: formation of a table of strategic macro-level analytics and graphical analytics for it, formation of the weight lists of analytics and the target mass range for the developed for the strategic and macro level, And third, formation of structural model and functional model at the strategic or micro level. 4. Construction the diagrams S and their derivatives for various levels of abstraction at the current milestone. The construction is performed on the basis of the section commercial data of the extended structural model. The levels of abstraction for which the diagrams can be constructed are given the column level of the extended structural model. The fifth, assessment of the degree of novelty of the product, the strategic micro level, using the generated functional model and analysis of the risk associated with increasing the level of novelty. See section economic indicators of the technical assignment for the project. 6. Formation of information for the relevant section of the technical requirements, technical assignment for product development using data from the table of analytics and the structural functional model, including the section technical and economic requirements, only for products as a whole, as well as the components and assemblies for which the technical requirements is formed. 7. Formation of a strategic action plan, consolidated or including local measures to reduce cost based on the results of applying the method of factor research or MFR. And we will describe the local level of design engineering. Value analysis and value design engineering can be attributed to direct design engineering tools for designing, making design decisions, and the local management of direct costs for a product. If it used to support design within the framework of the activities of the chief designer and the design department, through which the following functions can be implemented in the next ways. First, formation of a table of analytics of the local lower or micro level. Second, formation of a weight sheet of analytics and a target mass range for the strategic or macro level. Third, formation of structural and functional model at the local lower or micro level. 4. Determination of significance and relevance based on the degree of satisfaction of functions and quality of implementation of functions. 5th, builds diagrams for UAS and 6S and their derivatives based on the dependence of quality of implementation on the current milestone. 6. Assessment of the degree of novelty of the component at the local level using the generated functional model and analysis of risks associated with an increase in the level of novelty section, economic indicators of the technical assignment of the component. 7. Formation of information for the relevant sections of technical requirements and technical assignment for the development of a component using data from the table of analytics of structural and functional model, including the section technical and economic requirements for parts and simply assemble units. Technical assignment is usually not formed, but within the framework of the value analysis and value design engineering for any object of analysis an extended functional basis. The next, 8. Formation of a local action plan to reduce the cost of individual parts and assembly units based on the results of applying the method of factor research. Okay, that's all. In our today's issue, unmanned aircraft system is considered at the strategic or macro level. Therefore, we will not consider the mechanism and standard forms for determining satisfaction and quality of implementation. See theoretical issue number 12. Determining significance and relevance. See theoretical issue number 11. And charting AQS and 6x diagrams. And however, let's consider an example of generating information for technical requirements and technical assignment sections. See steps 9 and 10 of this issue. In order to form a top level or strategic functional model in accordance with the recommendations announced in issue number 10, we use the principle of one function carrier and one price, one costs. In this case of functional model formation of the middle lower levels of abstraction, I mean full functional model, the application of the principle of one function carrier, one function, one price, or one cost is allowed only at initial stages of functional model formation. Then the methods or independent formulation of functions is applied, i.e. the number of functions in the functional model becomes the number of function carriers, become more the number of function carriers by quantity. Let's consider the stages of filling in the fields of the basic functional models of unmanned aircraft system. The features of the formulation of functions in this case, they have already been formulated, and the introduction of formulations in the column function formulations for the basic functional model have already been discussed by us in issue number 7 of the theoretical course Cost Engineering, so I will not dwell on them, noting only two nuances. First, we work on the upper level of abstraction, therefore, in first approximation it's permissible to use the principle of one function carrier, one function, or one price. Secondly, the formulation of the function in this case shouldn't be made excessively concise, because it's on their basis that we will form the text part of the technical assignment. Let's consider the stages of filling the fields of the extended functional model of the unmanned aircraft system. In the part of the block containing information on the applied methods for determining the significance and relative relevance of functions, it's possible, similarly to basic model, to make a reference to issue number 11 of the theoretical course, since the listener who hasn't familiarized himself with the theory of determining significance and relevance obviously simply doesn't understand what the difference between the concept of significance and relevance and what is flowchart of table significance relevance, not to mention the choice of methods of determining significance. In accordance with the degree of abstraction of consideration, let's just say that the middle and the lower levels of abstraction, the selection of methods for determining significance is performed, then a flowchart of significance relevance or table significance relevance is built, and already on its basis the mentioned sections of the extended functional model are filled in. In the column standard deviation or relevance average, an asterisk of the column standard deviation of relevance average, or average relevance it means that the value of the standard deviation is given for reference, i.e. conditional verification of the value of direct costs in the column expert evaluation of direct costs for function. In fact, at the stage of filling the functional model fields, we estimate the value of the standard deviation twice. The first time when processing the survey data for significance and satisfaction and quality of performance, and the second time when evaluating the final value of the relevance of average relevance. See column standard deviation of relevance average. Since in this case we are considering the upper level product abstraction and determining the significance and relevance of function and their carriers for reason of impossibility of excluding any components from the full name column and the structural model and other reasons already voiced above isn't feasible, then we will consider an example of an alternative display in the flowchart significance relevance from issue number 11 in the format of the significance relevance table. The significance relevance table as field is based on the standard forms of assessment of significance and satisfaction, which we have already mentioned in issue number 12 of the theoretical course, and is thus a kind of intermediate, a link between the survey to access satisfaction and quality of implementation of functions and the functional model. Let's consider an alternative, or rather a tabular display of the significance relevance flowchart given in issue number 11 in more detail, since this form or block scheme This form will continue to be repeatedly used by us by analyzing parts and simple assembly units in combination with the standard form for determining the significance and quality implementation, in particular in practice case number 3. So, in the table of significance relevance shown on the screen, the hierarchical structure from the top-level assembly units to parts and their functions, unlike the flowchart, is directed not from top to bottom, but from the left to right. Accordingly to the conditional boundary of the engineering transition now becomes not horizontal as in flowchart, but vertical, and divides the table into two blocks or two areas: area on function carriers and area on functions. For each block of area, a list of their corresponding abstraction level is provided, as well as methods for determining the significance of functions in accordance with the table of significance methods discussed by us in issue number 11 of the theoretical course. The general order algorithm of filling and extended functional model at any level of abstraction has the following form. First, structural model and functional model are formed in accordance with the degree of abstraction, sets the stage of initial data for analytical works, functions are formulated. Next, the standard form of available significance relevance table is filled in, except for relative values of significance. The next, and accordingly with the wording of the function and functional model, standard forms for determining significance and quality of implementation are filled out. A short survey of the target group with a high statistical weight is conducted. In case B2C or D2C, a detailed interview with an external customer, says case B2B, or an interview of the working group in the case of analytical work within the company developer or manufacturers of the products. The next, data from the survey of significance, satisfaction and quality of implementation are being processed with an assessment of the standard deviation for various methods of determining significance. The values or relative significance are entered into the standard form of a table relevant significance, and the values of relative relevance are calculated for various methods from M2 to M20 and determining significance. The next, relative relevance values for various techniques from M2 to M20 are entered into the extended functional model. The average relative relevance for individual average relevance functions is calculated. The standard deviation for the average relevance value is estimated. And the last, based on the data obtained, combined calculation model is filled in. UAS and 6S diagrams are constructed, as well as various modifications of text and tabular analytics reports are prepared. Stage 9. Stage 9 includes the formation of the first approximation of the text form of the technical assignment based on structural and functional model formed on stages 7 and 8. Accordingly, the data in question should certain descriptions of the design engineering structure and basic consumer functions of the unmanned aircraft vehicle being developed in tabular or standard functional basis and textile extended functional basis view. Initially, I would like to recall the features of conditional data separation and structural functional models, as well as its meaning. The structural and functional models considered in stages 7 and 8 are divided into two parts, basic and extended respectively. These parts are painted over the different colors to improve visualization. Above the table is indicated basic structural and functional model, data for formation and technical requirements and technical assignment, and extended structural and functional model data for the formation of advanced analytics. Thus, when describing the process of technical requirements formation, we will mainly be interested in the basic part of structural and functional model. Before proceeding directly to the formation of a textual technical assignment, or rather its individual sections, which we conditionally designated as a functional basis in theoretical editions, it should be noted that in most cases technical assignment for a previous generation product is taken as a basis for creating a technical assignment for a new product. However, according to the terms of the case, our company decided on product development in a new niche. Therefore, in fact, the formation of technical assignment has to start from scratch. Therefore, it can be argued that the use of value analysis and value design engineering techniques allows us to form a broader information base of initial data for the formation of technical assignment in the conditions described in the case. I will not dwell on detail on filling our sections 1, 2, 3 of technical assignment, name and scope, basis for development, purpose of development, technical requirements. Firstly, because it was done in one way or another in issue number 10 of the theoretical part of course. Secondly, the sections relate to the conditional formal part of technical assignment, the completion of which doesn't require design of academic education. We only note that the list of analytics, the developed unmanned aircraft system, can be taken from the table of analytics already discussed above. Next, let's look at the procedure for filling in the section 4 of the technical assignment called Technical Requirements. The list of supporting documents for the formation or rather formulation of the section of technical requirements of the top-level technical specification or product specification in our case includes: first, airworthiness standard for the considered or close class of unmanned aircraft system, contained a large number of textual formulations of requirements for basic unmanned aircraft system units and systems suitable for technical assignment. Second, Federal Aviation Rules. In this case, Federal Aviation Rules number 21 and 61 application extremely limited as a rule. This documentation is used extremely to fill the sections requirements for patent purity, requirements for unification and standardization, and etc. Third, business plan. Fourth, value analysis and value design engineering analytics. Common initial data, structure and functional model, tables of analytics, and etc. Fifth, the results of additional R&D. In this case, we are talking about scientific research related to the level of novelty of the product, which will be discussed below in the section Economic Indicators of Technical Assignment. The assessment of the level of novelty is performed precisely by the tools of value analysis and value design engineering, which is extremely useful in assessing the amount of R&D which can be specified in particular in the business plan of the project. The logic in this case is simple. The higher the degree of novelty, the higher the value of additional R&D. And the sixth, other information from open sources, like scientific publications, manuals on the operation and development of unmanned aircraft system. Accordingly, based on this list, two consequences can be formulated. Consequence 1. The above list is a conditional algorithm for formation of technical assignment by the value analysis and value design engineering method, or in accordance with the generally accepted formulation, the formulation of technical assignment by the method corresponding to the concept of final price and design to cost. If you delve into the relationship to the design process and final pricing, then the value analysis and value design engineering methodology, generally speaking, corresponds to two methods: design to cost and pricing based on the value of features. Consequence 2. The difference between the technical assignment formed by the value analysis and value design engineering method in accordance with the concept of final pricing design to cost from the technical assignment formed by the conditional traditional design engineering method, i.e. without the support of design process by the cost engineers division, corresponding to the concept of cost pricing cost plus, is the presence of two auxiliary documents: the business plan, item 3 of the list, and the value analysis and value design engineering analytical report, item 4 of the list. To fill in subsection 4.1 technical assignment entitled Product Composition and Requirements for Unmanned Aircraft System, it's necessary to select the level of structural model according to which this section will be formed, and accordingly to the structure and contents section located on the second page of the technical assignment. As we can see, the second and third levels are most suitable, since they sufficiently reflect in structure, and at the same time we do not go to the level of individual units and systems that are purchased products, as it will be at the fourth level. If we choose the second level, then the concept of mechanical part will appear in the table of contents of technical assignment, which is quite abstract. In addition, if we turn to examples of technical assignment, then, for example, individual elements of the conditional mechanical part, such as the power plant and body, are separated into separate sections and indicated in the table of contents. In addition, a more detailed design engineering structure in the table of contents of the technical specifications visually gives a more detailed idea of the design of an unmanned aircraft system to any third-party specialist who needs to familiarize himself with the technical specifications. In view of all these arguments, the section product comparison and requirements of an unmanned aircraft system on the technical assignment will be formed in accordance with the third level of abstraction. To fill subsection 4.1.1 of the technical assignment basic parameters and characteristics, we use information from the analytic table we formed at stage 4, in particular the section general characteristics of the unmanned aircraft system of the analytic table already mentioned above. In addition, in the table of basic parameters and characteristics, if necessary, can include data from the local section's general characteristics as part of individual components or systems described in the table of analytics. In the first approximation of the formation of technical assignment, we will limit ourselves exclusively to the data from the section general characteristics of unmanned aircraft system of the table of analytics. To fill the subsection 4.1.2 of the technical assignment, named requirements of the power plant from the above supporting documents, we use airworthiness standards for unmanned aircraft systems with an unmanned aircraft helicopter with maximum takeoff weight up to 750 kilograms, as well as value analysis and value design analytics. I agree that the unmanned aircraft as part of the unmanned aircraft system considered in our case is quite far from 715 kilograms of takeoff weight. However, from the publicly available regulatory documentation, this document is the closest in design engineering features to the unmanned aircraft system we are analyzing, especially since we will only take individual formulations as a basis, without copying them verbatim. So, in paragraph UAS VT 901, the following wording is given. The unmanned aircraft system power plant considered in this section includes every component except the design of main and auxiliary propellers that it's necessary to create the power required for movement, controls the main propulsion system, ensures the safety of the propulsion system during periods between normal inspections and repairs. Accordingly, in the context of our task, only the part necessary to create the power required for movement can be used and should be taken into account respectively. Based on the formulation of the function of the carrier power plant, which sounds like to form a system for creating and implementing the available thrust force on the propeller, we can write in paragraph 4.1.2.1 of the technical assignment the following standard wording takes into account the context of our case. The electric propulsion system is designed to create and realize the available thrust force of the propeller by converting electrical energy into mechanical energy and creating mechanical impulse sufficient to overcome the unmanned aircraft vehicle air resistance and ensure translating motion or hovering. For the subcomponents of the power plant, the standard wording of the paragraph the component is intended for is made according to a similar principle based on formulation of the functional model. When formulating paragraph 4.1.2.2 of the technical assignment, as we can see, the design structure given in the table of analytics and duplicated in structural and functional models, including such constituent elements of an electric power as electric motors, electric engines, electric motor mounting system, propellers, electric motor control system. For other technical assignment components, the structural model of which is reflected in the table of analysis, and structural model the principle of forming a paragraph describing the constituent elements is similar. If there is no detailed description of the structure of the table of analysis and structural model, such as a pylon beam, due to the level of abstraction we have chosen, we can turn to alternative sources of information, starting from specialized software for technical benchmarking, see HMAC1 and analysis, ending with obtaining this information by independently dismantling the structural elements and describe it, as for example I can do with MGX Box 7, which was purchased in preparation for working on this release. Using a similar method based on airworthiness standards, paragraph from 4.1.2.3 to 4.1.2.6 are formulated, taking into account the correction for the takeoff, weight, and overall dimensions of the unmanned aircraft vehicle. For example, the need for metallization and its design engineering can be adjusted during further development, since it's difficult to choose standard jumpers for UAS of such dimensions, to put it mildly. In addition, in the case of using the other indicated in the table analysis of materials, time and flight speed, they may not be needed at all. However, as a first approximation, I propose to leave paragraph 4.1.2.5 on its current form. Among other things, I would like to note the possibility of using information from the weight list in the formation of technical assignment, which is in addition to the factors that exist in the design process as an independent document, is used, for example, when filling out the table calculated characteristics of the battery system, see section 4.1.4. In particular, the range of permissible masses is entered on this table from 0.068 to 103 grams, calculated by us in the column range of permissible masses on standard deviation at stage 5 of our case. Attention should be paid to the free section information labeling plates next to the case and the user software, which relate to exceptions in the sense they are not included in the structural model and functional model, being included to the section technical requirements of the text technical specification. The section information markings place isn't included in the structural and functional model in connection with the considered level of abstraction. Indeed, in rare cases, when forming the initial and most general possible structural and functional schema of the product, some remembers the place in the case. However, I wouldn't minimize the role, since on the fuselage on the closest analog on the MGX Box 7 and DJI reference models, plates and various inscriptions occupy a prominent place, in particular for security reasons as well as for advertising purposes. Thus, for lower level technical assignment, the section information marking place may well be included in the structural and functional models. The case section isn't included in structural and functional model due to the fact that in a full-fledged technical assignment, the review of the structure of which was carried out by us in issue number 10 of the cost engineering course, there is a standard section requirements for conversation, packaging and labeling, in which the requirements for the case should be indicated. Regarding the importance of the case when operating a small drone, for example at home, I can note based on my personal experience that its convenience is extremely important. The section user software isn't included in structural and functional model because in this case I am guided to the principle according to which in our case the components included the structural model must be physical carriers of functions, i.e. have mass dimensions, etc. In this case we approach the issue of the correctness of the application of the value analysis in relation to non-material objects of analysis such as software, the organizational structure of the enterprise, the functionality of the enterprise and the service sector, the resume of the applicant in HR, and etc. Despite the presence of a large number of scientific publications in which the value analysis is applied in various fields, I treat that issue extremely cautiously, since for each field in application, in my opinion, there is at least the nuance, the need to develop a new classification of functions. Indeed, the classification of functions used in mechanical engineering is likely to be suitable for the case forming a functional model for an enterprise in the service sector. See articles of the application on the value analysis in the service sector. Further filling in the text technical assignment is performed according to a similar principle by searching for the relevant sections in airworthiness standard, filling in the tables of required technical data, as well as referring to the materials prepared by us at the previous stages of analysis. The table of analysis, information of the technical characteristics of analysis, structural model assessment of the level of abstraction, a functional model formulation of basic functions of unmanned aircraft system components. Stage 10. Forming data for filling the section economic requirements of technical assignment. Since our case relates to the case of value analysis and value design engineering implementation at the strategic level or managerial level, with the corresponding highest level of abstraction on the construction of UAS and 6S diagrams for the highest level. As we have shown above, it's not correct due to the inability to accurately determine the values of significance, importance, degree of satisfaction, and the quality of performance of consumer functions. Then it's necessary to determine the list of information that can be included in the section Technical and Economic Requirements of the technical assignment. For unmanned aircraft system based on results of our analytical works at previous stages. The recommendations given in section 6.1.5 Technical and Economic Requirements of GOST 15016 have already been partly analyzed by us as part of the issue number 10 of the theoretical course. However, I suggest going back to them and performing an assessment in an applied content. In other words, making a table with a list of requirements and indicating the sources of information opposite each of them. So, in the first paragraph of section 6.1.5 of GOST 15016, it's indicated the following phrase. In the section Technical Economic Requirements, the requirements are established, the fulfillment of which will ensure the development of a product that meets the conditions of economic feasibility and its creation according to the criterion and efficiency cost. I suggest not to delve into this case the method of evaluating the efficiency cost criterion, because, as my analysis showed, firstly, for each industry, this analysis has its own calculation methodology and even its own name. For example, the analysis of performance indicators, the analysis on efficiency costs, etc. Secondly, the very concept of efficient is extremely vague, and it's also set by regulatory documents within industries or even individual companies. In general, what exactly developers of GOST 15016 had in mind to put in mind is not clear. In the table shown on the screen, we can see a list of standard and additional data that can be specified in section 6.1.5, Technical and Economic Requirements of the Technical Specification, GOST 15016. The content of paragraph 9 of the table presented on the screen, namely the wording. Technical and economic characteristics reflecting the advantages of the product being developed in comparison with the best domestic and foreign products of a similar type may correspond the following three types of output data of the value analysis and value design engineering as a strategic or macro level listed by us in the comments to stage 8. Table of analysis, structure and functional model, and the assessment of the degree of novelty of the product as a strategic or macro level using generated functional model and risk analysis. Let's consider each of the three types of value analysis and value design engineering output data separately. The first, the table of analysis is, in fairness, it's worth nothing that the table of characteristics of analysis is almost always present as a business plan, however, in much more simplified form than in the table of analysis formed within the framework in our case. More precisely, the business plan presents a list of the most important characteristics which obviously are interested to assess the effectiveness of the product being developed. Accordingly, this simplified list of characteristics of analysis in the business plan doesn't allow to form the design structure of the product as is done in our case. The second, structural and functional model. This type of value and analysis and value design engineering output data has already been used in the formation of the technical assignment structure corresponding to the design structure of the product being developed, see structural model, as well as the text part of the technical assignment describing the main functions of the product being developed at the macro level, see functional model. And the third, product novelty assessment and risk analysis in terms of analyzing the degree of novelty for the case of reverse engineering, especially at micro level. The obvious assumption is that below and above the level of the VR goggles that we added to the composition of the closest analog of MGX Box 7, it is 0. And the level of the VR goggles, fourth level, it's different from 0. All three listed types of output data can be included in the technical assignment in one way or another in various forms. First, information about analysis prepared on the basis on the table of analysis considered by us at stage 4 is included in section 5 technical and economic indicators of the technical assignment in the form of a table of reference characteristics of unmanned aircraft systems analysis. This table contains sections such as general characteristics in which analyses are evaluated in terms of reference in the class. In this case, DJI models are taken as a standard and the closest analog of MGX Box 7 V2. The methods of filling in this section of the table is an expert assessment by analysts and a working group. The section relative economic characteristics and relative function characteristics are filled in the data in the section selling price in retail, table of analysis and functional model respectively. The section technical specification is also filled in based on data from the table of analysis. With regard to the structural and functional model, it can be said that information from them will be reportedly entered in the form of a table of detection levels for considering the product being developed. Primarily, due to the bulkiness of table of structural and functional model and the resulting complexity of their perception, in fact, the mentioned table of detection levels of consideration of the product being developed is an excerpt from structural model. The assessment of the degree of novelty of the product and the risk analysis of the section 5.1 of the technical assignment is implemented in two types, tabular and textual. Firstly, in the form of table structure and functional technical novelty of the product under development, which is formed on the basis of structural and functional model analog of the product under development by determining the ratio of the number of new functions to the total number of functions. With regard to this table, it should be noted that despite its visual simplicity, its conditional slides of the quintessence of fairly large amount of analytical information. In addition, this table is a fairly visual managerial tool for comparing various designs, which can be used both when making design decisions and when preparing presentation for management for top level. Secondly, a comment to the minimum possible values of the technical novelty value will be introduced into the text part of section 5.1 of the technical assignment in the case of reverse engineering of unmanned aircraft system. The permissible minimum technical novelty at levels from 1 to 5 of the structural model should be 0% and higher. If we are carrying out a development that cannot be classified on its pure form as reverse engineering, then we can set a target value of the technical assignment for the degree of novelty of the product being developed, for example, from 5 to 10%, thus providing the product with an additional competitive advantage in the market. In this case, the introduction of VR glasses or helmet into the unmanned aircraft system gives us a value of technical novelty of the product equal to 2.5% as a fourth level abstraction corresponding to purchased products relatively simple assembly units and parts. In the case of the formation of technical specification for a system or an aggregate, as well in the case of formation analytics for purchased product or an assembly unit of a lower level, the table of structural and functional technical novelty of the developed product will look more diverse, since the changes of the lower levels of abstraction are more extensive. For example, we can add and exclude individual details, change technology manufacturing and the corresponding tolerances or roughness, and etc. At the upper levels, as we see on the example of our technical assignment, the table looks as concise as possible, which is logical since the exclusion of the top level objects from the design, especially in a reverse engineering situation, is unlikely. And indeed, we cannot exclude from the design the control panel, the spare parts or battery of the unmanned aircraft vehicle, since that will lead to the malfunction of the system. However, the issue of changeability and immutability of the system has already been considered by us above, and I see no point to dwelling on it again. Among other things, the text of section 5.1 of the technical assignment mentions design engineering risks caused by an increase in the degree of novelty in the product, and the conclusion that the competitive advantage of the product in the case of low value of technical novelty relative to analytics should be ensured by the following measures. Let's describe the following measures. A high level of localization of production, if there are protectionist policy and localization requirements of the target market. The second, lower selling price relative to analytics. And the third, an increased level of quantity relative to analytics. An example of filling in the section technical and economic requirements of the technical assignment is presented on the screen. In addition, I would like to note that according to development statistics, achievement advantages of analytics in the framework of reverse engineering is generally unlikely but possible, but only within the framework of a lower level value analysis and value design engineering, i.e. analysis of individual units, systems, assemblies and parts. One of the ways to achieve such an advantage is to use the method of factory search, which was considered by us in the framework of issue number 9 of the theoretical course. As part of the case study, reverse engineering for a local during engineering value analysis option, which according to my plans, which we presented in the next issue. We will be able to make sure that more information can be added to the technical and economic requirements sections, in particular the UAS and 6S reports, on the basis on which direct cost targets for individual components of aggregates, systems and assemblies can be formed. Thus, we come to another confirmation of the increased effectiveness of the use of value analysis and value design engineering in the framework of design rather than managerial activities, i.e. value analysis and value design engineering is more effective not within the framework of macro-levels analysis, i.e. the formation of a multi-level of technical assignment for a product, but within the framework of the formation of technical assignment for separate systems and aggregates. Maximum efficiency with minimal error and calculations is achieved respectively when analyzing individual parts, i.e. forming complete structural functional model of the lower level. Let me remind you that in scheme for evaluating the effectiveness of value analysis and value design engineering is quite simple and is shown on the first sheet of the F1 form. considered by us as a stage 2. In particular, it's equal to the ratio of the cost of conducting analytical work during the year to the annual economic effect of carrying out these works, for example, reducing direct costs per unit of production. Stage 11. The formation of final analytics. Since in today's issue, unmanned aircraft system is considered at abstraction levels from first to fifth, or in other words, at the strategic or macro level, at the stage 11 we actually generate an analytical report in accordance with the list of applicability of the value analysis and value design engineering at this level of abstraction. The report can be generated both in paper and electronic form, for example, in the form of text tabular document with comments. However, in practice, such reports are often provided in an editable format, i.e., simply as files that can be edited in a tabular or text editor. Thus, the generated final level 1 analytics for unmanned aircraft system includes first, a table of strategic or micro level analysis, second, the weight sheet of analysis and target mass range for developed unmanned aircraft system, third, structural and functional model of strategic or macro level, fourth, as diagrams for different levels of abstraction at the current milestone, and the fifth, the text part of the technical requirements, technical assignment sections devoted to the technical and technical economic requirements for the product, including the degree of novelty and the risks associated with it, which in our theoretical course was designated as an extended functional basis. Stage 12. Acceptance and revision of analytical reports. The acceptance and completion of analytical reports is carried out in accordance with the business processes operating in the customer's company. Typical stages of acceptance and completion of analytical reports include preparation of text report in the first approximation, the second, formation of comments from the customer's company, additional exclusion of individual reports, and the third, formation of the final report and the presentation for the company's management based on it. It's optional.
Based on the results of this case, it can be concluded that the use of value analysis and value design engineering tools for the formation of a technical assignment is a universal approach to supporting product development by the cost engineering division, and its versatility is due firstly to the fact that the technical assignment is a mandatory design engineering document, not only within the framework of United System of Design Documentation, but also and within the framework of all existing international systems of design engineering documentation, for example, ISO, ANCI, DIN, and etc. Secondly, the ability to cover various levels of abstraction, starting the product level, ending with the level of details in particular. First, at the upper or strategic level, direct product costs at milestones are managed by managing the context, the content of technical assignment, and the corresponding structural and functional model form of management. In this case, statement or tracking without the possibility of forming design engineering recommendations for correcting design engineering documentation at the milestones, not including design engineering documentation adjustment related to the replacement of suppliers of purchased products, price reduction by suppliers, etc. by commercial aspects. At the lower or local levels, for changeable components for which a technical assignment is informed, up to complete models, management is carried out by controlling the structural and functional model of component and generating analytics RQS and 6S. Form of management in this case, correction of design engineering documentation. The possibility of forming design recommendations for design engineering documentation correction at milestones. In addition to the announced conclusion, I would like to announce another goal of the implementation and publication of this case, namely attracting investments. The use of products, cost management, and reverse engineering techniques using value analysis and value design engineering tools can be automated and scaled by creating a specialized value analysis and value design engineering unit or department and concept personnel and etc., which we have already considered in issue number 2 of the theoretical course Cost Engineering. The basic criteria for assessing the investment attractiveness of automation and scaling of the application of reverse engineering techniques based on value analysis and value design engineering tools are: first, cost effectiveness of investments in automation and scaling of the application of reverse engineering techniques, and the second, the risk associated with the lack of theoretical elaboration and the applicability of the value analysis and value design engineering methodology in practice. With regard to the factor of the investment efficiency, automation, and scaling of the application of reverse engineering techniques, it can only be noted that an indirect factor confirming the effectiveness of investments in this case is the presence of unprecedented sanctions against domestic engineering enterprises, and as a result the need to perform reverse engineering of a significant number of facilities. Numerical calculation of investment efficiency requires additional initial data on the needs of engineering companies in such software, which I do not have at the moment and which are unlikely to become public. Another indirect sign of the need to perform reverse engineering is the availability in open sources of information about the activities of design engineering bureaus of the individual domestic machinery building enterprises. In the field of classical reverse engineering, manual or automated measurements, including 3D scanning, weighting, composition analysis, prototyping and testing with a subsequent revision of the design engineering documentation. Thus, it can be assumed that there is a market for classical reverse engineering support services which can be positioned as an addition to the classical reverse engineering system, which allows firstly to perform the formation of technical specification and secondly to implement either of the concept of designing parts and assemblies within the framework of targeting direct costs or design to cost concept or the concept of value design engineering with the corresponding methods of the final pricing for the product, cost plus, to cost, and functional pricing. The target group of consumers of reverse engineering support services using value analysis and value design engineering tools are the design engineering departments of machinery building enterprises that need either to support and improve the efficiency of the classical reverse engineering process or to create their own cost engineering division or value analysis and value design engineering department. With regard to the second risk factor associated with the lack of theoretical elaboration and the applicability of the methodology in practice, it can be noted that the theoretical part of the course, cost engineering, set out in sufficient detail, in my opinion. See issues from 1 to 14 of the training course. Cost engineering meets the minimum requirements for theoretical justification, both in terms of its volume and content, and in a format that allows you to train specialists of newly formed departments within a 10-hour theoretical course and practical cases that can be formed for a specific customer, taking into account the specifics of development of object. Regarding the possibility of automating the working standard forms for the value analysis and value design engineering division, the degree of their readiness is confirmed by the materials demonstrated in theoretical editions and practical cases. And if automation is necessary, it's only necessary to translate the existing standard forms of their internal formulas from the format of a tabular editor into the format of the required interface and implement the stage of bringing them to the conditional state of a minimally viable product or MVP. Examples of the practical application of reverse engineering techniques in combination with the value analysis and value design engineering tools for different levels, ranging from the level of the product as a whole to its individual components, aggregates, systems, and even parts, with presented in the framework of practical cases in the value analysis for cost engineers channel. I plan to choose the component of existing unmanned aircraft system as objects for reverse engineering within the framework of practical cases in connection firstly with my initial aviation profile and secondly with their accessibility and popularization of the direction of unmanned air aviation currently observed. Summing up the above, we can say that the investment goal is to implement a project to automate and scale the application of reverse engineering techniques using value analysis and value design engineering tools, as well to provide services for performing local analytical works or mini projects for target groups of customers in the field of aircraft engineering and other branches of mechanical engineering. If you are interested in joint implementation of projects, please write in person or fill out the feedback from the website costengineer.ru. That's all for today. Please put likes and subscribe. All bye.